Imagine this. You're floating in the middle of space. No sound. No gravity. Just an endless sea of darkness stretching out in every direction. Suddenly, far away in the distance, a tiny dot catches your eye. It's glowing blue. Not white. Not red. But a rich, piercing blue. And it's alive. It's not a star. It's not a planet. It's something much stranger. Something most people don't even know exists. It's called a Blue Compact Dwarf Galaxy. And what's going on inside that small, weird blue speck might just hold the key to some of the biggest mysteries in the entire universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. See, space is full of strange things. Black holes that eat entire stars. Planets that rain metal. Moons that shoot water like geysers. But sometimes, the weirdest mysteries aren't the biggest ones. Sometimes, the strangest things in the universe are the small ones hiding in plain sight. And that's exactly what Blue Compact Dwarf Galaxies are. They look tiny. They look quiet. But once you really start looking into them, they make you question everything you thought you knew about space, time, and how the universe even works. Let's break this down. First, a Blue Compact Dwarf Galaxy, also known as a BCDG, is a type of galaxy that's super small and packed with stars. But here's the twist, these stars are mostly brand new. We're talking baby stars, fresh, hot, and burning with energy. That's why these galaxies glow with a strong blue light. Because young, hot stars give off blue light. And there's tons of them. But hold on. That doesn't make sense, does it? In the universe, big galaxies usually have the most star formation. Think about massive spirals like the Milky Way, or the monster ellipticals at the center of galaxy clusters. Those are the places you'd expect to see star-making factories. But BCDGs? They're tiny. They shouldn't even have enough gas to make this many stars. And yet, somehow, they're doing it. Not just making stars, but making tons of them. Rapidly. Aggressively. Like something kicked them into overdrive. Scientists have been scratching their heads over this for decades. Where is all this star-forming gas coming from? Did they somehow get a sudden burst of it from another galaxy? Did they merge with something invisible? Or is there something deeper going on here that we still don't understand? Some researchers think these galaxies might be examples of what the early universe looked like. Back when the first stars were being born, things were chaotic. Clouds of hydrogen were collapsing all over the place. Light was finally breaking through the darkness. Maybe BCDGs are snapshots of that ancient era, tiny islands in space stuck in a cosmic time loop, repeating what the early universe once did. Others think they might be way older than they look. That the blue glow is just a distraction. Maybe they formed billions of years ago, and only recently got triggered into forming new stars. If that's true, then these galaxies are like sleeping giants, quiet for ages, suddenly waking up and going wild. And then there's the weirdest theory of all. That some of these galaxies shouldn't even exist. Their mass, their speed, their location, it just doesn't add up. In some cases, they're moving in ways that don't make sense based on gravity alone. Which leads to the big question, is dark matter involved? Because if you want to talk about true cosmic mystery, you can't avoid dark matter. The invisible stuff that makes up most of the universe, but we can't see it, can't touch it, and still don't know what it is. Some scientists believe that BCDGs are being shaped, maybe even created, by dark matter. That the reason they're acting so strange is because they're sitting in dense clumps of dark matter, being pulled and pushed by forces we don't fully understand yet. And if that's true, then studying BCDGs could be one of the best ways we have to figure out what dark matter really is. We're talking about solving one of the biggest puzzles in science. A puzzle that could change everything. But the mysteries don't stop there. Because when you zoom in on these galaxies, you start noticing other weird things. Like how the star formation isn't always even. Sometimes, one side of the galaxy is packed with new stars, and the other side is almost dead. That's not normal. And it hints at something violent going on. Maybe a collision. Maybe a jet of gas slamming into it from somewhere else. Or maybe a hidden black hole is stirring things up. Yes, even in these small galaxies, there's evidence that black holes might be hiding in their centers. That's another thing that scientists never expected. We used to think black holes were only in big galaxies. But now, we're finding clues that even these tiny galaxies might have them. And if they do, it raises a big question: how did they get there? Because black holes don't just appear out of nowhere. They grow. They feed. They need time. And yet, some BCDGs seem to have powerful black holes already in place, despite being so small, despite being full of young stars. So were those black holes born early? Did they form before the stars? Or did they come from somewhere else entirely? And here's another twist. Some BCDGs aren't isolated. They're in groups, like little clusters of small galaxies orbiting each other. And sometimes, they seem to be interacting, pulling gas from each other, crashing together, creating waves of new star births. It's like a miniature version of what happens on a huge cosmic scale, but it's all happening in this strange, compressed environment. And then there's the question of how common they really are. For a long time, we thought BCDGs were rare. But new telescopes, like the James Webb Space Telescope and others, are starting to pick up more and more of them. Hidden in the shadows. Faint. Compact. But everywhere. That suggests these galaxies might be way more important than we ever realized. Maybe they played a key role in the early universe. Maybe they're still shaping it now. And let's not forget something crucial. These galaxies are some of the best laboratories we have to study the life cycle of stars. Because they're filled with brand new stars, we can observe what happens during those early stages. How they burn, how they interact, how they explode. In a way, they let us look back in time and watch the story of the universe unfold and fast forward. But even with all the data we've gathered, even with all the theories we've built, the truth is, we still don't fully understand them. Every time we think we've got it figured out, a new discovery pops up and throws everything into chaos again. And that's what makes Blue Compact Dwarf Galaxies such a deep, mind-bending mystery. Because they force us to confront the fact that space isn't just strange, it's stranger than we can imagine. That the universe is still hiding secrets in the smallest corners. And that sometimes, the tiniest, weirdest galaxies out there might be the ones holding the answers to the biggest questions of all. Some theories suggest that BCDGs might be merging with smaller, gas-rich galaxies that we just can't see clearly from Earth. These invisible or barely visible companions could be feeding them with the gas they need to kickstart star formation. Kind of like a silent partner in a business, staying hidden but making all the action possible. But even that doesn't explain everything. Because many BCDGs seem isolated. No nearby galaxies. No obvious signs of interaction. Yet they're bursting with newborn stars. So if it's not a merger, what is it? That leads to another mystery. These galaxies aren't just making stars. They're doing it in intense, short bursts. Scientists call this a starburst. Picture this: a galaxy suddenly lights up like fireworks, producing stars at a crazy fast rate, then settles down again. It's not a slow, steady process. It's more like a cosmic explosion. But why? What makes a tiny galaxy flip a switch and go full throttle? And here's where things get even weirder. Some BCDGs don't even seem that young overall. The galaxies themselves could be billions of years old. But for some reason, they're forming young stars now. That means they've been sitting there for eons, quietly existing, then all of a sudden, boom, massive star formation. Like a volcano that stayed silent for centuries and suddenly erupted. So now we've got a bunch of questions on the table. Why are these small galaxies forming stars so fast? Why now? Where did the gas come from? And how long can they keep this up? Let's talk about their size. These galaxies are tiny compared to most others. Some of them are only a few thousand light years across, which is minuscule in cosmic terms. For comparison, the Milky Way is over 100,000 light years wide. That's like comparing a small town to an entire continent. But despite their small size, BCDGs pack a serious punch. Their cores are often crammed with young stars, dense clouds of gas, and intense radiation. Now here's something crazy. Because of how bright their young stars are, blue compact dwarf galaxies can sometimes be seen from really far away, even though they're small. That means we've been able to spot some of them in the distant universe, giving us clues about what early galaxies might have looked like. In a way, studying BCDGs is like looking back in time. They could be snapshots of how galaxies behaved billions of years ago, right after the Big Bang. And this brings us to one of the most mind-blowing ideas. Some astronomers think that BCDGs might be some of the last galaxies still forming stars the way early galaxies did. Think about that. In a universe that's constantly changing and evolving, these tiny blue galaxies could be fossils of a forgotten age. Still burning. Still alive. Still making stars like it's the early universe. That gives them huge scientific value. If we can understand BCDGs, we might understand how the very first galaxies formed. We might uncover secrets about the birth of stars, the flow of cosmic gas, and how matter clumps together in the void of space. But there's more. Some BCDGs have extremely low amounts of heavy elements. In astronomy, anything heavier than hydrogen or helium is considered a metal. And these galaxies have very little of that. Which makes sense. Because metals are formed by older generations of stars. If a galaxy is forming stars for the first time, or hasn't formed many before, it won't have had time to build up a lot of metals. That's why BCDGs are sometimes called chemically primitive. But that just makes them more interesting. They could be among the purest galaxies we've ever seen, like untouched pieces of the early universe. And that raises a whole new set of questions. Could these galaxies help us study what matter was like shortly after the Big Bang? Could they give us a window into the first generation of stars, known as population 3 stars, that we've never directly seen? Some scientists think so. If we find the right BCDG, it might contain clues to these ancient stars. Maybe even light patterns or gas compositions that hint at their existence. There's also the question of their future. If BCDGs are burning through gas so fast, won't they run out soon? And what happens then? Do they fade into quiet, dark galaxies with no more star formation? Or do they somehow gather more gas and light up again in another burst? We don't fully know. Some researchers believe they may go dormant for long periods, only to reawaken when the right conditions line up. Kind of like a heartbeat that pulses every few billion years. Another strange thing, BCDGs don't really fit into the neat boxes we use to classify galaxies. They're not spirals. They're not ellipticals. They're not irregulars in the traditional sense. They're kind of their own thing. Some of them do have irregular shapes, twisted asymmetric, like a splash of paint. Others are more compact and round. But what unites them is their brightness, their size, and their intense blue glow. And get this, some of these galaxies are almost completely isolated in space. Far from any major galaxy cluster. No big neighbors. Just them, drifting alone in the cosmic sea. Yet they're still forming stars, still lighting up the darkness. That isolation just deepens the mystery. Because you'd think that interactions with other galaxies are what kickstarts star formation. But in these cases, there's no sign of those interactions. It's like these galaxies have their own internal clock, ticking away, deciding on their own when it's time to shine. There's even evidence that some of them might have massive black holes at their centers, despite being so small. That blows a huge hole in what we thought we knew. Because we used to believe that only big galaxies could form big black holes. But if tiny galaxies like BCDGs can do it too, then we've got to rethink how black holes grow, where they come from, and what that means for the evolution of galaxies in general. It's also worth pointing out that BCDGs challenge our understanding of dark matter. Their behavior, how stars move, how gas is distributed, often doesn't make sense unless there's a lot of invisible mass holding them together. That mass is thought to be dark matter. So by studying these galaxies closely, we might get more clues about what dark matter is and how it interacts with normal matter. And just when you think it can't get more complicated, guess what? Some BCDGs seem to be interacting with dark galaxies. These are theoretical galaxies made almost entirely of dark matter, with little or no stars. If a BCDG bumps into one of these, it might trigger a starburst, even though we can't see the thing it collided with. That would explain some of the isolated BCDGs that suddenly light up with no obvious reason. They might be giving us a front row seat to how things began. Think about that. These tiny, blue, weird galaxies that barely take up space in a telescope image could be time machines. They could be showing us what galaxy formation looked like not long after the Big Bang. That's what makes them so important. We're not just looking at strange galaxies, we're looking at pieces of history frozen in time. But here's something even more mind-bending. A lot of these galaxies have very low metal content. And in astronomy, metals means anything heavier than helium. That's important because stars create metals as they age. So if a galaxy has low metal content, it usually means it hasn't had a lot of older stars in the past. It hasn't been through many star cycles yet. It's chemically primitive, which basically means it hasn't evolved much. And that throws another curveball into the mix. Because you'd expect an old galaxy to be chemically rich, full of heavy elements from previous generations of stars. But BCDGs aren't like that. They have old stars, sure. But they also look weirdly young in their chemistry. Like someone hit the reset button on them at some point. Or maybe they've been sitting in isolation, not forming many stars for billions of years, until something happened recently to trigger all this action. That raises a big question. Could BCDGs actually be examples of ancient galaxies that somehow avoided change for most of cosmic history? Some researchers think yes. They believe these galaxies formed a long time ago, then spent most of their lives in a kind of deep sleep. No major mergers. No big bursts of star formation. Just quietly drifting through space, unnoticed. Until something finally stirred them awake. Maybe they fell into a denser region of the universe. Maybe they ran into a clump of gas. Whatever it was, it jump-started star formation. And now we're catching them in the middle of that rare event. Others have a different theory. They think some BCDGs could be forming for the first time. That these galaxies are actually young, not just chemically primitive. That we're watching brand new galaxies in their infancy. If that's true, then BCDGs might not just show us the past. They might be showing us what galaxy formation looks like right now, in our own cosmic backyard. Which is kind of wild, because most galaxy formation happened billions of years ago. The idea that new ones could still be forming today flips a lot of assumptions upside down. And now, let's talk about how chaotic these little galaxies are. You'd expect something small to be calm, right? But nope. BCDGs are full of turbulence. Their gas clouds are getting smashed together, torn apart, pushed by winds from exploding stars. Supernovae go off like bombs, blowing bubbles through the galaxy and sending shockwaves across space. Some BCDGs have such strong outflows of gas that it looks like they're bleeding material into the void. That makes things even more confusing, because if they're losing gas, how are they still forming stars? One possibility is that they're constantly pulling in more gas from outside. Maybe from the intergalactic medium, that thin soup of particles floating between galaxies. If that's the case, then BCDGs might be plugged into a cosmic fuel line we don't fully understand yet. A kind of invisible umbilical cord keeping them alive, letting them defy the rules that should apply to tiny galaxies. That's a huge deal. Because it hints at a deeper structure in the universe. Something that channels matter into places we don't expect. And there's still more. Because when you look closely at these galaxies, they don't all follow the same pattern. Some BCDGs are round, others are irregular. Some have multiple clusters of star formation. Some have complex gas structures. That suggests there's no single story behind them. There might be dozens of different paths that lead to something becoming a blue compact dwarf. And that's where things get really mysterious. Because if these galaxies can form in so many different ways, then maybe they're not one kind of object at all. Maybe Blue Compact Dwarf Galaxy is just a label we slap on a bunch of very different things that happen to look similar for now. Which leads to the big question. What are we really looking at when we study these galaxies? Are they failed giants that never grew up? Are they newborns? Are they ancient relics? Are they temporary states of something else entirely? The truth is, we don't know yet. We have theories. We have data. But no solid answers. And that makes BCDGs one of the most exciting frontiers in astronomy. Because every time we point a telescope at one of them, we see something new. Something that challenges what we thought we knew about how galaxies work. They're small. They're bright. They're chaotic. They're confusing. And they're probably teaching us things we don't even realize yet. The idea that new galaxies could still be forming in the modern universe is pretty surprising, and kind of exciting. It suggests that the universe might still have a few tricks up its sleeve. Maybe galaxy formation isn't something that stopped a long time ago. Maybe it's still happening, just quietly, in little corners of the cosmos where no one thought to look. That leads us into another mystery. Why do BCDGs appear so isolated? Most galaxies are part of clusters or groups. They interact with neighbors, bump into each other, and tug on one another with gravity. But many BCDGs don't seem to have any nearby friends. They're just floating out there, doing their thing, far from the hustle and bustle of galactic life. That's odd. Because interactions are one of the main triggers for star formation. Two galaxies get close, their gas clouds collide, and boom, new stars light up. But if BCDGs aren't being disturbed by other galaxies, then something else must be setting them off. Could it be dark matter? That mysterious stuff we can't see, but know is out there, shaping the universe with its gravity? Some scientists think dark matter halos might be responsible. They believe these halos could compress the gas in a dwarf galaxy, forcing it to collapse and form stars. It's a hard theory to test, but it would explain a lot. Like how these galaxies get their starbursts without any obvious external trigger. Or maybe it's something even stranger. Like internal processes we don't fully understand yet. Something inside the galaxy itself, maybe a cycle of gas cooling and collapsing, could be starting the whole chain reaction. That would make BCDGs not just interesting, but totally unique. Galaxies that can ignite themselves, with no outside help. And we haven't even touched on the role of supernovae yet. These exploding stars play a big part in shaping BCDGs. When a star goes supernova, it sends shockwaves through the galaxy. Those shockwaves can compress nearby gas, creating new stars. But they can also blow gas away, slowing down star formation. It's a delicate balance. Too many supernovae, and the galaxy might lose all its fuel. Too few, and there's nothing to kickstart new stars. Somehow, BCDGs manage to walk that line, keeping their starbursts going without destroying themselves in the process. But that can't last forever. Eventually, they'll burn through their gas. When that happens, the star formation will stop, and the galaxy will begin to fade. Over time, it might become just another faint smudge in the sky, a fossil of what it used to be. Some researchers think many of the faint dwarf galaxies we see today might actually be the after version of BCDGs. Their starburst days are long gone, and now they're just quietly fading into the darkness. So in a way, studying BCDGs is like catching a galaxy during a rare moment in its life. Like seeing a firework go off in slow motion. It's dramatic, beautiful, and brief. And that's part of what makes them so fascinating. We don't know how long the show lasts, or what happens after the lights go out. All we know is, when we see one, we're witnessing something special. And then there's the question of their shape. Most BCDGs don't have the neat spirals or clean ellipses that bigger galaxies do. They're messy, lumpy, chaotic. That's because they're so full of energy. Starbursts, winds, radiation, it all stirs things up. The gas clouds get shredded and reshaped. The stars get flung around. The whole galaxy becomes a cosmic storm. And in that storm, we get to see the raw power of star formation in its most extreme form. What's also interesting is that BCDGs seem to come in a few different types. Some have a central core where most of the star formation happens. Others are more spread out, with bursts popping up in different parts of the galaxy. Some look like they've had recent mergers. Others look untouched. That variety makes them hard to categorize. They don't fit neatly into the usual boxes astronomers use. which means they force us to think differently, to come up with new ideas, to question what we thought we knew about galaxies. And here's where things get really wild. Some BCDGs show signs of having massive black holes at their centers. That's surprising, because we usually associate those with big galaxies. The idea that a tiny galaxy like a BCDG could harbor a black hole millions of times the mass of the Sun? That challenges a lot of what we thought about black hole formation. Maybe black holes don't just grow in big galaxies. Maybe they can start in small ones, too. Or maybe they've been there all along, waiting quietly until something triggers their activity. If BCDGs really do have black holes, it opens up a whole new set of questions. How did they get there? Did they grow slowly over time? Did they form early in the universe? Are they affecting the starbursts? Could they be helping to stir up the gas, or even trigger new star formation? There's so much we don't know. And that's why astronomers are so fascinated by them. Every time we look at a BCDG, we see something new. A new question. A new mystery. A new piece of the puzzle. And speaking of puzzles, BCDGs are also helping us understand dark matter. Because these galaxies are so small, the effects of dark matter are easier to study. Their rotation curves, the way stars and gas move inside them, don't make sense unless there's something invisible holding them together. That's dark matter. And by watching how BCDGs spin, we can learn more about how dark matter behaves on small scales. Some BCDGs also show strange velocity patterns, motions that don't line up with what we'd expect. That could mean their dark matter halos aren't smooth. They might be clumpy or off-center. And that could give us clues about the nature of dark matter itself. Is it cold? Warm? Interacting? BCDGs might help us find out. All of this makes BCDGs more than just weird little galaxies. They're test labs, natural experiments, cosmic snapshots. And because they're relatively nearby, at least compared to most other galaxies, we can study them in detail. Use powerful telescopes. Measure their gas, their stars, their movements. Piece by piece, we're slowly figuring out what makes them tick. But even with all the data, there are still so many unanswered questions. Are BCDGs common throughout the universe, or are they rare? Are they all the same age, or do they span a wide range? Do they evolve into other types of galaxies, or fade away completely? Are they the remnants of something larger, or the seeds of something yet to come? Blue Compact Dwarf Galaxies are one of those cosmic mysteries that just won't let go. The more we learn about them, the more questions we find. They're small, but their impact is huge. They force us to rethink how galaxies form, how they evolve, and what they can become. They challenge our models, break our assumptions, and push us to dig deeper. And maybe that's the most important thing about them. Not just what they are, but what they make us do. They make us curious. They make us ask better questions. They remind us that the universe is still full of surprises. Once a blue compact dwarf galaxy runs out of gas, it can't form new stars anymore. The bright blue glow that gives it its name will fade. What's left behind is a galaxy full of older stars, dimmer, redder, and much less energetic. Over time, these galaxies could evolve into something that looks completely different. Maybe a faint, red, elliptical galaxy. Maybe something so dim it's barely detectable. That's part of what makes studying them so urgent, because their current, blazing bright state is temporary. We're catching them in a flash, a cosmic blink, and once that phase ends, they'll never look the same again. But here's where it gets even weirder. Some BCDGs show signs that this isn't the first time they've lit up. They might have had past starbursts millions or even billions of years ago. Then gone quiet. Then lit up again. And again. Almost like they're pulsing. Like a heartbeat. That throws another wrench into our understanding of how galaxies evolve. We used to think that a galaxy forms stars steadily over time, then slows down as it ages. But BCDGs are showing us a different story, one of stops and starts, bursts and silences. Why does that matter? Because if galaxies can go through these phases, maybe other galaxies we see today went through something similar in the past. Maybe even our own Milky Way had a few intense starburst phases in its history. And if we don't study BCDGs while they're in the middle of one of these phases, we'll miss our chance to understand what those phases look like. That's why astronomers keep pointing their telescopes at them, trying to catch every detail, every cluster, every cloud of gas, every supernova blast. And we're learning more all the time. With new instruments like the James Webb Space Telescope, we can now look inside BCDGs in ways we couldn't before. We can see individual stars, map out the gas, and trace the chemical fingerprints left behind by generations of star formation. We can compare them to early galaxies in the distant universe and ask, are these things truly primitive? Or just pretending? That's not an easy question to answer. Because BCDGs are full of contradictions. They look young, but hold old stars. They seem isolated, but show signs of interaction. They're simple in structure, but complex in behavior. They're small, but their implications are massive. And then there's their sheer variety. Not all BCDGs are the same. Some are extremely compact, like glowing knots of gas and light. Others are more spread out, with tails or irregular shapes that hint at past collisions or close encounters. Some are violently active, forming stars at a furious rate. Others are a little more laid back, glowing softly with fewer newborns. That diversity makes them even more difficult to categorize. It's like trying to study one type of animal, only to realize that each individual behaves completely differently. But it also makes them fascinating. Because every BCDG has its own story. Take their shapes, for instance. Many BCDGs are irregular, no clear spiral arms, no obvious symmetry. That's usually a sign that something dramatic happened to them. Maybe they were pulled apart by gravity. Maybe they absorbed another dwarf galaxy. Or maybe they just never had the conditions to form neat, orderly structures in the first place. Whatever the reason, their messy shapes make them stand out. They look chaotic, but maybe there's a deeper pattern underneath all that chaos. And then there's the question of how many BCDGs actually exist. We've found a few hundred of them nearby, within a few 100 million light-years. But the more we look, the more we find. And with better technology, we'll likely uncover thousands more. Some might be hiding behind dust, or buried in crowded regions of the sky. Others might be so faint that we've missed them completely. Which means we could be looking at just the tip of the iceberg. The BCDG population could be far larger than we think, and that would have huge implications for how common these galaxies really are in the universe. And maybe, just maybe, some of them hold clues to even deeper questions. Like how the first galaxies formed. Or what the early universe was really like. Or how dark matter shapes the cosmos. In fact, some scientists are starting to wonder if BCDGs are the ideal place to look for new physics. Not just new galaxies, but new laws of nature, hidden in plain sight. That's a big claim. But think about it. These galaxies exist in environments with very little pollution from heavy elements. That means they're cleaner, purer, more like the universe was shortly after the Big Bang. That makes them perfect testbeds for theories about how stars and galaxies first formed. And if those theories don't match what we see in BCDGs, then maybe the theories are wrong. Maybe we've been missing something all along. And here's another twist. Some BCDGs might actually be key to understanding cosmic reionization, the moment in the early universe when light from the first stars and galaxies began to ionize the hydrogen gas around them. That was a crucial turning point in cosmic history. But we still don't know exactly which galaxies were responsible. Some researchers think BCDGs, or galaxies like them, might have played a major role. Why? Because they leak radiation. They're full of young, hot stars that blast out ultraviolet light. And in some cases, that light escapes into space, unfiltered by dust or gas. That's exactly the kind of light that would have driven reionization. So when we study BCDGs today, we might be seeing echoes of that ancient era. We might be learning how the universe transformed from a dark, neutral place into the complex, glowing web we see now. That's not just cool, it's essential to understanding our origins. And speaking of origins, what about the future? What happens to these galaxies after the starburst fades? Do they fade into obscurity? Do they merge with other galaxies? Do they get torn apart by gravity, their stars scattered into space? That's still up for debate. Some models suggest that BCDGs evolve into dwarf elliptical galaxies, rounder, redder, and more passive. Others suggest they might become something completely new, depending on their environment and history. But no matter what path they take, one thing is clear: BCDGs are not just background noise in the universe. They're signals. They're signposts. They're cosmic wildcards that challenge everything we thought we knew about how galaxies live and die. And the deeper you go, the more questions you find. Why do some BCDGs form stars so efficiently, while others don't? Why do some lose their gas quickly, while others keep it for billions of years? Why do some show clear evidence of past interactions, while others appear untouched? Are we looking at one phenomenon, or many different ones that just happen to look similar? We don't have all the answers yet. But that's what makes this so exciting. Every BCDG we study brings us one step closer to understanding the big picture. Not just how galaxies work, but how the universe itself works. These small, scrappy, glowing galaxies are punching way above their weight. And they might just hold the key to unlocking the biggest mysteries of space. And that's what makes them so endlessly fascinating. They force us to question what we think we know about galaxy formation, cosmic timelines, and even the behavior of matter itself. Let's dive deeper into those contradictions. When you look at a BCDG, the first thing that jumps out is the bright blue color. That's a clear sign of young, hot, massive stars burning through their fuel at a breakneck pace. These stars live fast and die young, sometimes in just a few million years. But when we peer past the brightness and analyze the starlight more closely, something surprising shows up. There are older, redder stars hiding in the background. They're faint, but they're there. That means the galaxy isn't new. It's just having a very dramatic moment right now. So why do these older stars matter? Because they tell us something about the galaxy's past. A galaxy with only young stars would suggest that it was just born, maybe recently pulled together from a cloud of gas. But if there are old stars too, then that galaxy's been around for a while. It's just going through a late growth spurt. That breaks a lot of our assumptions. We thought small galaxies formed their stars early and quietly faded out. But BCDGs show us that some of them stayed quiet for billions of years, and are only now starting to light up. That delay is weird. What could cause a galaxy to wait billions of years before forming stars? Maybe it didn't have enough dense gas at first. Maybe it was in a calm patch of space, with nothing to trigger star formation. Or maybe, just maybe, it's because of something even more exotic, like cosmic filaments. These are giant strands of dark matter and gas that stretch across the universe. Galaxies tend to form along these filaments. And it's possible that a BCDG drifted into one recently, picked up a fresh supply of gas, and suddenly had everything it needed to start a burst of star formation. But even that raises questions. If a galaxy is getting a fresh supply of gas, where is that gas coming from? Is it left over from the Big Bang? Is it being pulled from nearby intergalactic space? Or is it being stolen from other galaxies, maybe even through invisible bridges of dark matter? Astronomers have been puzzling over these questions for decades, and we still don't have all the answers. What we do know is that BCDGs aren't just oddballs. They might actually be clues, little windows into how the universe works at a deeper level. Some scientists believe that by studying BCDGs, we can better understand what the earliest galaxies were like. After all, the early universe was a chaotic place. Galaxies were small, unstable, full of gas, and forming stars like crazy. Sound familiar? That's exactly what BCDGs look like. It's possible they're modern-day analogs of ancient galaxies, frozen in time. That idea is especially intriguing because it means we don't have to rely only on deep space observations to study the early universe. We can look closer to home, at galaxies just a few million light-years away, and learn the same lessons. It's like finding a time capsule in your backyard. And then there's the chemical mystery. Most galaxies, especially big spirals like the Milky Way, are full of metals. Not the kind you'd find in a junkyard, but metals, in the astronomical sense, anything heavier than hydrogen or helium. These elements are forged inside stars and spread around by supernovae. Over time, a galaxy's gas becomes more enriched with metals as more stars live and die. But BCDGs buck the trend. Even though they've formed stars, sometimes in multiple bursts, they're still very metal poor. That's strange. It's like they've missed out on billions of years of chemical evolution. Why haven't they built up more metals? Are there supernovae blowing the metals out into space? Are they somehow inefficient at recycling material? Or are they constantly pulling in fresh, metal-free gas from outside? Any of those could be true. But we don't know for sure. What we do know is that this metal-poor environment makes BCDGs even more like the earliest galaxies, which had nothing but hydrogen and helium to work with. And that's another reason astronomers study them so closely. They let us test our models of star formation in pristine conditions. Even their structure is puzzling. Most galaxies have some kind of order, spirals, bulges, disks. But BCDGs often look like messy blobs. No clear spiral arms. No big central bulge. Just a clump of bright stars, surrounded by a fuzzy halo of older stars and gas. And sometimes, even the gas distribution looks lopsided or disturbed. That's led to theories that some BCDGs are the result of mergers. Two or more dwarf galaxies crashing together and triggering a burst of star formation. That would explain the irregular shapes and sudden starbursts. But again, not all BCDGs show signs of mergers. Some seem to have lit up all on their own. That brings us back to the bigger picture. What are blue compact dwarf galaxies really telling us? They're telling us that the universe is messier than we thought. That star formation doesn't always follow a straight line. That even tiny galaxies can surprise us. And most importantly, they're telling us that we still have so much left to discover. Because the more we study BCDGs, the more mysteries we uncover. How do they regulate star formation? Why do some seem to have dark matter halos, while others don't? What causes some to shut down and others to flare up again? Are they truly isolated, or are we just not seeing their faint companions? Are they common or rare? Are they on their way to becoming something else? Or are they the last of their kind? And that's just one type of galaxy. In the grand tapestry of space mysteries, blue compact dwarfs are just one strange thread. But pulling on that thread might unravel deeper truths about the universe itself. Because if we can understand how these tiny galaxies live, evolve, and die, we might finally start to understand how everything else fits together. See, when astronomers say, primitive, they're not being insulting. They're talking about chemical composition, specifically, how much heavy elements, like oxygen, carbon, iron, are present in a galaxy. Those heavy elements are only created inside stars. When stars explode, they scatter these elements into space, where they mix with gas clouds and become part of the next generation of stars. So the more star generations a galaxy has had, the more heavy elements it contains. But BCDGs often have incredibly low levels of these heavy elements. Some of them are among the most metal-poor galaxies we've ever found. That suggests something wild. Either these galaxies haven't formed many stars yet, or they've somehow avoided enriching their gas with metals even after forming stars. Both possibilities are hard to explain. If they haven't formed many stars, why not? What stopped them for so long? And if they did form stars, where are the metals? Did the metals get blown out into space by supernova explosions? That's actually a real possibility. Because BCDGs are small and their gravity is weak, they can hold onto gas as well as larger galaxies can. When a star explodes in a massive supernova, it sends shockwaves and high-speed particles flying out in every direction. In a tiny galaxy, that might be enough to blast gas right out into intergalactic space, taking metals along with it. This kind of violent blowout might be happening right now in some of the BCDGs we're observing. Astronomers have seen giant gas bubbles expanding away from the cores of these galaxies, clear signs of powerful stellar winds and recent supernova activity. That could explain why their gas stays so pristine. But it also hints at something else. These galaxies might be slowly destroying themselves with every starburst. Think about that. Each time a BCDG forms a bunch of stars, it lights up, glows brilliantly, and becomes visible across vast distances. But in doing so, it also risks blowing away the gas it needs to form future stars. That means the very thing that makes it visible, its brightness, is also what might end its ability to shine in the future. This balance between creation and destruction is like walking a cosmic tightrope. Too few stars, and the galaxy stays dark and invisible. Too many, too fast, and it risks burning itself out. And because these galaxies are so small and delicate, even small changes can have huge consequences. A nearby supernova, a collision with a passing gas cloud, or even a change in pressure from the surrounding space could tip the scales. And that brings us to one of the biggest mysteries of all. Where did these galaxies even come from? Are they leftovers from the early universe, small pieces that never grew into full-sized galaxies? Or are they fragments of larger galaxies that were torn apart by tidal forces? There's evidence for both theories. Some BCDGs have irregular shapes and chaotic internal structures, suggesting that they've been disturbed or pulled apart by gravity. That fits with the idea that they're the remnants of galactic collisions or interactions. Others look surprisingly smooth and symmetrical, as if they've been quietly existing in isolation for billions of years. That fits more with the idea of primordial relics, tiny galaxies that somehow survived unchanged since the dawn of time. What makes this even more confusing is that we've also found BCDGs that seem to exist in both environments, some in dense galaxy clusters, others all alone in empty parts of the universe. That means there's probably no single origin story for these galaxies. Instead, Blue Compact Dwarf Galaxy might be more of a description than a category, a label we slap on any small galaxy that happens to be undergoing a sudden starburst and glowing with intense blue light. And yet, despite how rare they are, and how odd they behave, BCDGs might hold some of the most important clues to how the universe evolved. Because they're small, they show us how star formation works in environments without the complexity of large galaxies. Because they're metapolar, they let us study conditions similar to the early universe. And because they're bursting with energy, they give us a front-row seat to one of the most dramatic processes in the cosmos. What we're learning from them doesn't just apply to dwarf galaxies. It ripples out into our understanding of cosmic structure, galactic evolution, and even how life-supporting elements came to be. And that's not an exaggeration. The heavy elements created in starbursts like the ones in BCDGs eventually become the building blocks of planets, water, air, and even our bodies. So by watching these galaxies, we're watching the universe create the ingredients for life. And that raises a mind-bending possibility. Are there planets in these galaxies? Could life exist in a BCDG? That's a tough question. Most BCDGs are so chaotic and unstable that it seems unlikely. Starbursts produce a lot of ultraviolet radiation and supernova explosions, both of which are extremely hostile to life as we know it. The stars themselves are often too young to have formed planets, or if planets did form, they might not have had enough time to develop complex chemistry, let alone biology. But then again, the universe is full of surprises. We've found planets around all kinds of stars, big ones, small ones, old ones, even dead ones. If planets can survive in other extreme environments, maybe they can survive in BCDGs too. Maybe there are rocky worlds orbiting older, cooler stars in the outskirts of these galaxies. Maybe they've been there for billions of years, quietly waiting. And maybe, just maybe, they're watching their own sky and wondering the same thing we are. Burning itself out entirely. It's a fragile, temporary phase. A brief moment in cosmic time when everything aligns just right for a spectacular burst of life before fading into quiet darkness again. And that might be exactly why blue compact dwarf galaxies are so rare. We're catching them in a tiny window of time, a brief phase that doesn't last long. Most of the time, these galaxies are probably too faint or inactive to even notice. Only during these outbursts do they shine bright enough for our telescopes to spot them. It's like watching a firefly in a dark forest, blinking on just long enough to catch your eye, and then disappearing again into the night. But here's the part that really twists the brain. Some scientists believe that BCDGs might be the closest analogs we have to the very first galaxies in the universe. Let that sink in. Billions of years ago, after the Big Bang, the universe was filled with gas, mostly hydrogen and helium. Heavy elements didn't exist yet. The first stars were made of pure, primordial gas, and the galaxies they formed in were tiny and chaotic. These early galaxies would have been low in metals, bursting with new stars, and highly unstable. Sound familiar? That's basically the definition of a BCDG. So in a strange way, studying BCDGs is like looking back in time. Even though these galaxies exist in the modern universe, their behavior and composition may be mimicking what the very first galaxies were like. They offer a window into the deep past, a chance to observe a process that shaped the early cosmos, but in a setting close enough to actually study in detail. That's why researchers pay so much attention to them. These galaxies might help us answer some of the biggest questions in cosmology. How did the first galaxies form? How did they evolve? How did they start producing the elements that make planets and life possible? And the clues keep piling up. In some BCDGs, astronomers have found clues suggesting they contain some of the lowest metallicity stars ever discovered, meaning these stars are made of almost entirely pure hydrogen and helium. These could be what scientists call population 3 analogs. Population 3 stars are a hypothetical class of stars that formed right after the Big Bang. We've never seen one directly, but if they existed, they would have been huge, hot, short-lived, and crucial to creating the first heavy elements. BCDGs might contain second-generation stars formed from the remnants of those early giants. It's hard to overstate how important that is. If we can study these ultra-metal-poor stars in BCDGs, we might be able to reconstruct the timeline of chemical evolution across the universe, from the very first atoms to the ingredients of life on Earth. We're talking about connecting the dots between the birth of stars, the creation of elements, and the eventual rise of intelligent life. All through the lens of a tiny, faint, chaotic galaxy. And just when you think BCDGs can't get more bizarre, there's another layer. Some of them don't even seem to belong where they are. Astronomers have found isolated BCDGs, galaxies sitting out in the middle of nowhere, with no neighbors for millions of light years. That's a mystery. Because one of the ways we think BCDGs start starbursts is by colliding or interacting with other galaxies. Gravity slams them together, compresses their gas, and triggers new stars to form. But if a BCDG is isolated, with nothing nearby, what caused its sudden burst of activity? That's the million-dollar question. Some theories suggest they might have absorbed gas from cosmic filaments, or that a hidden black hole or dark matter interaction sparked something internally. Others suggest they might not be as alone as they look. There could be faint, undetected gas clouds around them that helped ignite the burst. Whatever the answer is, it's clear that BCDGs refuse to follow the rules. And that's what makes them so exciting. In a universe full of massive, predictable spiral and elliptical galaxies, these tiny rebels break the mold. They're chaotic, explosive, and fleeting, but they hold the keys to cosmic history. And if that's true, then Blue Compact Dwarf Galaxies aren't just quirky, mysterious little fireballs in space. They're cosmic fossils. Living relics of the early universe. Time capsules floating in space, carrying the signatures of ancient processes we can't observe anywhere else. Now, let's pause for a second and think about the scale of what that means. We're talking about objects that might hold the answers to how everything we know today began. Galaxies that are still burning today, billions of years after their first ignition, offering clues to a time when stars were first learning how to shine. It's almost poetic, these tiny galaxies, largely ignored for decades, now turning out to be some of the most important cosmic laboratories we have. But the mystery only deepens from here. Because even though we've made huge strides in understanding BCDGs, there's still a long list of questions we haven't answered. For example, where do they come from in the first place? One theory is that they form from interactions, tiny galaxies bumping into each other and stirring up enough gas to ignite new starbursts. That could explain why many BCDGs look disturbed or lopsided. Some show signs of tidal tails, warping, or even double cores, hinting that they might be mid-collision or just recovering from one. And while most of these interactions happen on a much smaller scale than what we see in big galaxy mergers, the basic idea is the same: gravitational chaos triggers rapid change. But here's the weird twist. Some BCDGs appear totally isolated. They're just out there, sitting alone in space with no neighbors in sight. No obvious sign of a collision. No tidal streams. Nothing. So where did their starbursts come from? This has led to other ideas. Maybe these galaxies accrete cold gas from the intergalactic medium. Over billions of years, they slowly pull in pristine hydrogen from their surroundings. Then, for whatever reason, perhaps a small shockwave or internal instability, that gas suddenly collapses and forms stars in a short, violent episode. It's like a cosmic sneeze, nothing, then BM, stars everywhere. Or maybe they've been forming stars in slow motion all this time, but something triggered a runaway effect, where one generation of stars sets off the next, leading to a domino chain of ignition. That might explain why some BCDGs seem to wake up after being dormant for eons. But this just leads to another question: why now? Why are we seeing these galaxies lighting up right now, in the current age of the universe? Most galaxies formed long ago and have settled down. So why are these little guys still having major growth spurts? It's like finding a baby in a nursing home. It doesn't quite fit. And then there's the strangest possibility of all. What if BCDGs didn't evolve from ancient galaxies at all, but are actually new? What if, against all odds, some of these galaxies formed recently, in our cosmic backyard, from leftover gas that just hadn't clumped together before? That idea shakes things up. It challenges the assumption that all galaxies are old. It suggests that galaxy formation might still be happening today, in quiet corners of the universe where conditions are just right. And if that's true, then BCDGs could be the newest kids on the cosmic block, not relics of the past, but newborns of the present. The problem is, both ideas, ancient fossil and modern newborn, are supported by different pieces of evidence. Some BCDGs have very old stellar populations lurking beneath their bright new starbursts. Others seem to lack older stars entirely. Some have large gas halos, while others appear stripped and depleted. There's no one-size-fits-all answer. Every time we study a new BCDG, it adds a twist to the story instead of tying up loose ends. And that's exactly why scientists are obsessed with them. Because in science, the best mysteries are the ones that don't fit neatly into any box. The ones that force us to rethink what we thought we knew. BCDGs are doing that right now. They're small, but they're blowing holes in our understanding of galaxy evolution. They're rare, but they may hold keys to universal truths. They're quiet for billions of years, and then suddenly they scream. And we just happen to be watching during one of those screams. So what does the future hold for our understanding of these galaxies? For one, telescopes like the James Webb Space Telescope are helping us peer deeper into them than ever before. With its insane sensitivity and infrared vision, JWST can spot the faintest old stars hiding behind all that bright new star formation. It can study the chemical makeup of the gas, figure out how enriched it is, and maybe even detect direct signs of those elusive population 3 analog stars. It's like turning on a flashlight in a dark attic. You suddenly see all the stuff that was always there but just out of reach. Meanwhile, surveys with telescopes like Hubble, the Very Large Array, and upcoming instruments like the Square Kilometer Array are mapping the environments around BCDGs. Are they really isolated? Are there faint gas streams feeding them? Are they slowly cannibalizing smaller clouds? Every new discovery paints a richer, more complex picture. And there's even talk of studying them using gravitational lensing. If we can find faraway BCDGs whose light has been bent and magnified by foreground galaxies, we might get super high-resolution views of their structure, without needing even bigger telescopes. That could unlock whole new layers of detail about how they work. But even with all this technology, the biggest breakthroughs might come from something simpler: asking better questions. Blue Compact Dwarf Galaxies aren't just an astrophysical curiosity. They're a mirror. A reflection of cosmic cycles, of growth, destruction, rebirth, and silence. They remind us that the universe isn't static. That even the smallest things can be loud. That even after 13.8 billion years, creation is still happening. And that, honestly, might be the most awe-inspiring part of all. And this is where things get really wild. Some scientists have proposed that blue compact dwarf galaxies might be proof that star formation isn't as predictable as we thought. In massive galaxies like the Milky Way, star formation tends to follow a more or less steady process. You've got huge spiral arms packed with gas, dust, and stars, and everything sort of feeds into this ongoing cycle. But in BCDGs, that cycle is chaotic. It's not a gentle churn, it's a series of explosions, pauses, and reboots. That chaos actually challenges some of our models of galaxy evolution. If small galaxies can keep reigniting themselves like this, it means they may contribute more to the overall structure of the universe than we've accounted for. Traditionally, the focus has been on big, bright galaxies because they're easier to study. But if BCDGs are constantly forming new stars in sudden bursts, then they could be responsible for a bigger chunk of star formation than we realized, especially in the early universe. There's also another angle that makes these galaxies even more interesting: dark matter. BCDGs seem to have a lot of it. Because they're small, you'd expect them to be fragile, easily pulled apart by gravity, collisions, or even internal starbursts. But many BCDGs are surprisingly stable over long periods of time. That suggests there's something holding them together. Something with mass, but no light. That something is dark matter. In fact, in many BCDGs, dark matter may outweigh normal matter by a huge margin. Some estimates suggest that 90% or more of the galaxy's total mass is invisible. And that's not unique to BCDGs. Dark matter is common in all galaxies. But in these tiny systems, it becomes especially noticeable. It's like putting a marble on a trampoline and realizing the dip it causes is way too deep. There's something else beneath it you can't see, pulling harder than you'd expect. This makes BCDGs prime targets for dark matter studies. If we can understand how dark matter behaves in these small galaxies, how it clusters, how it moves, how it interacts with gas, we might get one step closer to solving one of the biggest mysteries in science: what dark matter actually is. And then, there's the structure inside these galaxies, which only adds to the complexity. You'd think something this small and chaotic would be just a random clump of stars. But that's not always the case. Some BCDGs have central star clusters so compact and bright they mimic the core of much larger galaxies. Others have strange asymmetries, off-center starbursts, or tails of gas and stars trailing into space. Some are spherical, others are elongated, some are ring-shaped. There's no single template. Every BCDG seems to be doing its own thing, which makes cataloging and comparing them really difficult. And that's where things begin to take on a more philosophical tone. Because the more we learn about these galaxies, the more they seem to break the rules we thought were universal. They're tiny, but they burn with the intensity of giants. They're young and old at the same time, some made of brand new stars, others harboring ancient cores. They're isolated and yet somehow full of fuel. They follow some patterns, but break others. And no two are exactly the same. So what are they really? Are they failed galaxies, ones that never managed to grow past a certain point? Are they ancient survivors, untouched by the violence of cosmic history? Are they newborns, just now lighting up for the first time? Or are they something else entirely, an evolutionary stage we barely understand, part of a process that's happening all over the universe in slow motion? That's the puzzle. And maybe the best part is that we don't have the full answer yet. We're still discovering new BCDGs every year, still learning how they tick. Each one we study gives us a little more insight, not just into dwarf galaxies, but into the universe itself. Into how things began. Into why galaxies form the way they do. Into what the early universe might have looked like, and how it changed into the cosmos we see today. And that brings us back to the broader theme of space mysteries. Because if something as small as a blue compact dwarf galaxy can hold secrets about the birth of everything, then what else is out there, hiding in plain sight. What other tiny, overlooked objects might turn out to be the missing pieces of some bigger cosmic puzzle? The universe is a vast, echoing place, full of shadows, whispers, and half-finished stories. And sometimes, the quietest voices end up telling the most important tales. Chaotic would be a mess on the inside. But surprisingly, that's not always the case. Some blue compact dwarf galaxies show incredibly well-defined central regions, almost like mini-nuclei. Others have star clusters spread throughout, like bright freckles scattered across their small frames. Some even have spiral-like structures, but on a much smaller and tighter scale. It's like taking a full-sized galaxy and compressing it down to a fraction of its size, but keeping a lot of the same visual complexity. The gas distribution in these galaxies is another big mystery. Hydrogen, the raw material for stars, often extends far beyond the visible light in BCDGs. You can look at one through a telescope and think, okay, here's the galaxy. But when you map the hydrogen, you find this enormous, ghostly halo of gas surrounding it, sometimes 10 times larger than the visible portion. It's like finding out a matchstick has a smoke cloud the size of a stadium. And here's where the questions multiply. Why do these galaxies have so much gas, but form so few stars most of the time? Why do they hoard their fuel for billions of years, then suddenly use a bunch of it all at once in a quick burst, only to go quiet again? Some researchers think magnetic fields might be playing a role. In larger galaxies, magnetic fields can help regulate star formation by pushing against gravity and slowing down the collapse of gas. Maybe something similar is happening in BCDGs. Or maybe not, maybe we're missing something entirely. Maybe we don't even fully understand how gas behaves on these smaller scales yet. But then you get into the question of why they look blue. That part, at least, is relatively straightforward. The blue color comes from young, massive stars. These stars are extremely hot and burn through their fuel in just a few million years, emitting mostly blue and ultraviolet light. So when you see a BCDG glowing blue, it means you're catching it in a moment of intense youth, cosmically speaking. It's like seeing a baby take its first steps, brief, energetic, and full of potential. And yet, just beneath the surface, many BCDGs have an older stellar population too. Faint red stars, low mass and long-lived, hiding behind the brilliance of the young ones. This mix of young and old stars creates a kind of duality in BCDGs. They look like newborn galaxies at first glance, but underneath, they're ancient survivors. It's this hidden depth that keeps scientists fascinated. They look simple, but they're not. Now let's talk about location, because where these galaxies live in the universe also adds to the intrigue. Some are found in isolation, way out on the fringes of galaxy clusters, drifting like cosmic nomads. Others are nestled in more populated regions, surrounded by larger galaxies. And in some cases, we've found small groups of BCDGs orbiting each other, interacting, and potentially merging over time. And even though they're small, their starbursts can be extremely powerful. Some BCDGs produce so many supernovae in such a short period that they launch huge winds, cosmic outflows of gas blasting away from the galaxy at hundreds of kilometers per second. These winds can strip a BCDG of its star-forming fuel, basically shutting it down for future bursts. But they can also spread elements like oxygen and carbon into the intergalactic medium, helping to enrich the universe as a whole. So in a way, BCDGs are both creators and destroyers. They create stars, spread elements, light up dark patches of the universe, and then sometimes self-destruct, or fade into dormancy. They burn bright, burn fast, and leave behind a different galaxy than they started with. Every time one of these galaxies bursts into life, it rewrites its own future. And here's a thought that might keep you up at night. What if our own galaxy used to be like this? What if, billions of years ago, the Milky Way was a tiny, chaotic burst of blue light, a small compact galaxy just beginning to build itself? What if blue compact dwarf galaxies aren't rare, but just early versions of something that eventually grows up into a spiral or elliptical galaxy? That would mean these little firecrackers aren't just anomalies. They're the beginning of everything we know. And we're only scratching the surface. You think you're looking at something new, something just getting started. But really, you're looking at something that's been around for billions of years, something that's just decided to light up again. It's like finding an old, silent volcano that suddenly erupts. It's not new, it's just reawakened. That duality is what makes Blue Compact Dwarf Galaxies so strange and captivating. They don't fit neatly into any box. They aren't fully young, but they aren't fully old. They aren't massive, but they aren't insignificant. They aren't common, but they aren't exactly rare either. They seem to live on the edge of understanding, the edge of visibility, and the edge of what we can explain. And they don't just challenge our ideas about galaxy formation, they challenge our assumptions about time itself. Because if a galaxy can sit for billions of years doing almost nothing, then suddenly explode into a frenzy of activity, what does that say about cosmic timelines? What does it say about how long we should expect galaxies to stay quiet or active? What else might be lurking in the darkness, just waiting for the right moment to shine? That's why astronomers are obsessed with finding more of these galaxies. Every new blue compact dwarf galaxy we discover is like opening a new mystery box. What's its structure like? How many stars is it forming? How old are those stars? How much gas does it have? What's its chemical makeup? Is it isolated, or is it interacting with a neighbor? Is it in a group of galaxies, or floating out there all by itself? And when we start answering those questions, even more pop up. Like, why are BCDGs so chemically primitive? Most of them have very low levels of heavy elements, things like carbon, oxygen, nitrogen, and iron. That's a huge clue because those elements are created in stars and spread through the galaxy when stars explode. If a galaxy has very little of those elements, it suggests it hasn't had many generations of stars. So now we're looking at galaxies that could be relics from the early universe, still carrying the chemical fingerprints of a time when the universe had barely started to make complex elements. That's why some scientists think BCDGs might be living fossils, preserving the conditions of the early cosmos in a way that larger, more evolved galaxies just can't. But there's still more. Because some blue compact dwarf galaxies might not even be natural at all. At least not in the way we usually think of natural. Some astronomers have started wondering whether these galaxies are the leftovers of bigger galaxies that were torn apart. Maybe they were once part of a larger structure, but something, like a massive gravitational interaction, ripped them to pieces, and what we're seeing now is a remnant core that flared up again. If that's true, then BCDGs are more than just quirky, blue-lit oddballs. They're survivors. Remnants. Cosmic orphans. Fragments of galactic violence that somehow managed to hold on to their identity. And here's the twist that keeps scientists up at night. If BCDGs are this complex, this varied, and this surprising, how many of them have we missed? Because they're small, faint, and often hidden in more crowded regions of the sky, they're hard to detect. We've probably only scratched the surface. For every BCDG we've found, there might be dozens or even hundreds more out there, invisible to our current surveys, waiting to be discovered. Some might be even weirder. Some might be closer than we think. And some might hold answers to the biggest cosmic questions we've ever asked. What is dark matter? How do galaxies form? Where did the first stars come from? What happens when a galaxy dies and comes back to life? Blue compact dwarf galaxies might not look like much at first glance, but they could be the key to everything. And that's why we can't stop looking for them, studying them, questioning them. Because in a universe filled with giants, sometimes the smallest things hold the biggest secrets. Some of them have relatively high amounts of heavy elements, way more than you'd expect for galaxies of their size and age profile. And that completely messes with the idea that they're pristine remnants of the early universe. It's like finding a caveman holding a smartphone. Suddenly, you realize maybe your entire assumption about their origins needs to be rethought. Where did these metals come from? Did these galaxies once have a massive round of star formation long ago, lost their gas, and are now reigniting after a long dormancy? Or were they somehow enriched by external sources? Maybe absorbing gas expelled from a nearby galaxy or through a merger we haven't fully detected. And then there's the role of dark matter. That invisible, mysterious force that we know exists but can't see or touch. The structure and survival of dwarf galaxies, especially these compact, active ones, may depend heavily on how much dark matter they contain. Since they're so small, their gravity alone wouldn't be enough to hold them together if dark matter wasn't present. They'd fly apart from the energy of their own starbursts. So astronomers suspect that BCDGs are sitting in cocoons of dark matter, protective, stabilizing halos that help them survive these chaotic episodes of star birth and gas blowouts. But we don't know for sure. And that's the frustrating part. We've never directly detected dark matter. We only see its effects. We see how galaxies rotate faster than they should. We see how gravity bends light around invisible masses. We see how clusters of galaxies behave in ways that normal matter alone can't explain. But when it comes to BCDGs, the dark matter halo idea is still just a theory, one that matches the math, but still needs proof. Even the environments these galaxies live in raise more questions than answers. Some BCDGs are found in isolation, far from any other galaxies. Others are nestled in galaxy clusters, surrounded by giants. And both settings seem to produce similar-looking galaxies. That's weird. You'd expect isolated BCDGs to evolve differently than those constantly influenced by their larger neighbors. But nature doesn't always follow the neat scripts we write. Sometimes it throws curveballs just to remind us we don't have it all figured out. And let's not forget the possibility that these galaxies are part of something even bigger that we can't fully see. Some astronomers believe BCDGs might actually be the visible tips of much larger gas clouds, like the glowing cap on top of an enormous, invisible mushroom. What we observe might just be the lit-up region, where a burst of stars formed. But beneath that glow could be a vast, hidden structure that spans far beyond what our telescopes currently detect. That would make every BCDG a kind of iceberg, most of its mass hidden in the cold darkness, waiting to be uncovered. The idea that these tiny galaxies could actually be part of something vast and mostly invisible is just another layer in the mystery. It forces us to look again at what we think we know about scale in the universe. Sometimes, big things come in small packages. Sometimes, what looks like a minor player turns out to be holding a much bigger secret. And in the case of blue compact dwarf galaxies, those secrets could stretch all the way back to the beginning of everything. Now think about this. In our own local universe, relatively close by in cosmic terms, there are hundreds, maybe thousands of dwarf galaxies. Many of them are invisible to us because they're faint and diffuse. But some of them, especially the BCDGs, make themselves known by lighting up suddenly. That means that at any moment, a new BCDG could flare up in a burst of star formation, like a cosmic firework going off in the void. And we wouldn't even know until it happened. It makes you wonder how many are hiding out there right now, on the verge of waking up. How many dormant dwarfs are waiting to flicker back to life and tell us a new story. And every time we find a new one, we're reminded just how little we really know. Each new observation brings us closer to understanding not just BCDGs, but the broader patterns of galaxy formation, star birth, and cosmic history. These tiny, intense, rebellious galaxies are like footnotes in the story of the universe that turn out to be the key paragraphs. They're strange, unpredictable, and often overlooked, but they might just be the most honest pieces of the cosmic puzzle we've got, hidden beneath the limits of our current telescopes. Imagine an iceberg, where all we can see is the glowing top peeking out of the water. Below that is a huge structure made of gas, dark matter, and perhaps even dim stars that aren't bright enough to register on our instruments. If that's true, then everything we think we know about BCDGs, their size, mass, and behavior, might be incomplete. We might be studying the flashy surface of something much deeper and older. That would completely change our models, because it means these galaxies aren't just small, compact blobs of chaos. They might be windows into massive, hidden structures playing by their own rules. The idea that blue compact dwarf galaxies are iceberg-like is supported by the discovery of massive reservoirs of cold hydrogen gas surrounding some of them. This gas isn't emitting light, but it can be detected through radio waves. In some cases, the amount of gas is far greater than the number of stars, meaning the galaxy could form many more stars in the future, or that it's sitting on potential it'll never fully use. It also suggests that what we see glowing is just the latest burst of activity, and not necessarily the full story. That quiet, invisible hydrogen cloud could have been there for eons, waiting for a spark, a galactic interaction, a shockwave, or just gravitational instability, to kick things into motion. And when that ignition happens, it's like watching the galaxy catch fire. Starbursts and BCDGs aren't subtle. They produce clusters of massive, hot stars that burn bright and die fast, often in supernova explosions. These supernovae not only spread heavy elements into the surrounding space, but also push against the galaxy's own gas, sometimes driving it out entirely. That's what makes the life of a BCDG so dramatic. It's not a steady process. It's explosive, chaotic, and often destructive. It's like the galaxy is constantly balancing between birth and destruction, building stars while simultaneously tearing itself apart. But somehow, despite all that violence, some BCDGs manage to survive. They go through these episodes and then settle back into periods of quiet. The gas settles, new stars fade, and everything goes dim again. Then, after millions, or even billions, of years, the cycle might start all over. This idea of galaxies having on and off phases challenges how we think about galactic life cycles. We're used to imagining galaxies as either active or dormant. But BCDGs blur those lines. They exist in between states. And that makes them incredibly useful for understanding the timing and triggers behind star formation across the universe. Another strange thing about BCDGs is their shape. Most large galaxies have clear structures, spirals, bulges, disks, bars. But BCDGs tend to be irregular. Some look like lopsided clouds, others like glowing knots of light. There's often no symmetry, no predictable patterns. That could be because of their small size and chaotic internal dynamics, or it could be a result of gravitational interactions in the past. Either way, their irregular shapes make it hard to categorize them, and they rarely fit cleanly into the traditional Hubble galaxy classification scheme. They defy the order we try to impose, and that alone makes them stand out. Their irregular shapes also hint at something else: mergers. When galaxies collide or interact, their shapes distort. Stars get flung around, gas gets compressed, and chaos reigns. It's possible that many BCDGs are actually the result of past collisions between even smaller galaxies. That would explain their strange shapes and sudden starbursts. Two gas-rich dwarf galaxies collide, compress their gas, and trigger a firestorm of new stars. In that sense, BCDGs might not be galaxies in their first phase of life, but actually the product of multiple smaller ancestors merging together in a cosmic act of creation. What's even more mind-bending is that some of these mergers might be happening right now, at the very edges of what we can observe. Deep sky surveys have started to uncover more and more compact galaxies with odd features, tails of gas, companion clouds, or multiple starburst regions. These could be BCDGs mid-transformation, caught in the act of becoming something new. And because they're small, these mergers happen quickly. On cosmic timescales, they're over in a flash. That means we have to be incredibly lucky to catch one in progress, which makes every discovery of an active BCDG even more important. And this brings us to one of the biggest reasons why blue compact dwarf galaxies matter so much to astronomy. They help us understand how the earliest galaxies in the universe might have behaved. When the universe was young, less than 1 billion years old, there were no big, mature galaxies. Everything started small. Galaxies had to grow from tiny clumps of gas, merging and evolving over time. In a way, BCDGs today might be giving us a glimpse of what those baby galaxies were like back then. Their low metallicity, chaotic shapes, and bursty star formation all resemble what we expect from early galactic structures. But there's a twist. Because the early universe was much denser and more active than today, some scientists argue that modern BCDGs aren't perfect analogues of the first galaxies. The conditions are different now. There's more dark energy, less ambient radiation, and galaxies are more spread out. So while BCDGs might look like ancient galaxies, they're still living in a modern context. That complicates things. It means we can't just assume they're direct time machines to the past. We have to account for how today's universe shapes their behavior, too. Still, even with those caveats, BCDGs are some of the best tools we have for studying primordial galaxy evolution. They let us test models about how stars form in metal-poor environments. They help us explore the effects of intense radiation on gas clouds. They show us how small galaxies can survive, and sometimes even thrive, in a universe that's dominated by giants. And because they're relatively close to us compared to the edge of the observable universe, we can study them in more detail than ancient galaxies billions of light years away. And then there's the question of fate. What happens to blue compact dwarf galaxies when they burn through their gas? Do they simply fade into small, dim dwarf ellipticals, cold and quiet, drifting through the void? Or do they get consumed by larger galaxies, torn apart and absorbed into the outskirts of spirals or ellipticals? Some astronomers believe that many of the faint, featureless dwarf galaxies we see today might actually be the remnants of once active BCDGs. In that sense, we might be looking at the final stage of their evolution, ghosts of a brighter, more violent past. But others think there's more to the story. Some BCDGs might cycle between bursts indefinitely, never settling down completely. As long as they have access to gas, either from internal reserves or external infall, they can keep reigniting, even after long quiet periods. That idea is wild because it means a BCDG could remain alive for tens of billions of years, much longer than most other galaxies. It might just sit quietly in the dark, waiting for its next big moment. That changes how we think about longevity in the universe. And this loops back to something we touched on earlier, how blue compact dwarf galaxies force us to rethink time itself. They're not consistent, predictable machines. They don't follow a steady pattern of growth or decay. They're erratic, surprising, and deeply complex. That makes them frustrating to study but also incredibly rewarding. Each one is a puzzle, and the more we learn, the more pieces we discover that don't quite fit. But maybe that's the point. Maybe BCDGs are nature's way of reminding us that not everything can be neatly sorted or explained. That some things are meant to be mysterious. Blue compact dwarf galaxies throw a wrench into that idea. They show us that galactic activity isn't always linear. It doesn't always go from young to old, from chaotic to peaceful. Instead, some galaxies flicker like cosmic fireflies, bursting into life, going quiet, then sparking again. That unpredictability makes them some of the most fascinating objects in the universe. It also makes them incredibly hard to model, because you can't just apply one timeline to all of them. Each one might have a different history. Some might have gone through multiple starburst cycles. Others might be on their very first. Some might be fading forever. Others could be just getting started. And that opens up a much deeper question, one that astronomers are only just beginning to explore. What does the life cycle of a blue compact dwarf galaxy actually look like from beginning to end? If we could watch one of these galaxies from the moment it formed until its final breath, what would we see? Would it go through dozens of bursts? Would it merge with something bigger and disappear? Would it collapse under its own gravity or simply drift through space forever, dim and forgotten? Right now, we have no complete answer to any of that, because we've only caught glimpses, snapshots in time. Every BCDG we study is like a single frame in a long, silent movie we haven't seen the beginning or end of yet. Some theories suggest BCDGs might be the missing link between the early universe and the modern one. They might show us what the first galaxies looked like before the large spirals and ellipticals took over. In that sense, they're like living fossils. But unlike bones buried in rock, these fossils are alive and changing. That's what makes them so powerful to study. They aren't static. They're still writing their own stories. And by watching them carefully, we might learn not only how galaxies like the Milky Way came to be, but how galaxies evolve in general. There's also a philosophical angle to all of this. When you look at a blue compact dwarf galaxy, you're seeing something that defies easy categories. It's small, but mighty. It's old, but active. It's simple in shape, but complex in behavior. It reminds us that the universe isn't neat and orderly. It's messy. It's unpredictable. And sometimes, the most interesting stuff isn't the biggest or the brightest, but the things that don't quite fit the pattern. That's where discovery happens. That's where we learn something new. And the more we look, the more we realize BCDGs might not be rare at all. They might just be hard to spot because they're small and faint, especially when they're not in a starburst phase. Our instruments tend to pick up the loud, flashy galaxies. But with new technology, especially radio and infrared telescopes, we're starting to detect more of these compact dwarfs hiding in the cosmic background. And with each one we find, our map of the universe becomes a little more detailed, and a lot more mysterious. These galaxies force us to stop and reconsider our assumptions. They make us ask questions like, what makes a galaxy important? Is it size? Age? Mass? Or is it the story it tells us about the universe itself? In the case of BCDGs, their value doesn't come from being grand or famous. It comes from being odd. From being different. From challenging the very systems we thought we understood. In a way, they are the rebels of the galactic world, quietly existing in corners of the cosmos, pushing back against what we thought we knew about how the universe works. As we get better tools, like the James Webb Space Telescope and other future observatories, we're going to be able to study BCDGs in ways we've never done before. We'll see deeper into their structure. We'll be able to track their star formation more precisely. We'll be able to measure their chemical makeup and understand how much metal they've produced over their lifetime. And that's crucial, because metallicity tells us a lot about a galaxy's history. A low metallicity galaxy, like most BCDGs, hasn't gone through many star-forming cycles. It means the elements that get forged in stars, like carbon, oxygen, iron, haven't had many chances to build up. That's why studying them gives us a kind of time machine effect. It's like seeing how galaxies behaved billions of years ago, back when the universe was still figuring itself out. But there's still another twist in the story. Some scientists think that BCDGs might be a temporary phase, not a permanent type of galaxy. Think about that for a second. We call them Blue Compact Dwarf Galaxies, as if that's their identity. But what if it's just a short chapter in a much longer book? What if every BCDG is just a regular dwarf galaxy caught in a flash of dramatic activity? That would mean this category we've built, this entire label, might not be describing a permanent structure at all. It could be like calling someone a teenager. It tells you something about what's happening right now, but not about where they came from or where they're going. It's a phase, not a definition. If that's true, then we have to rethink how we classify galaxies. We can't just group them based on what they look like in one moment. We have to think about how they behave over time. And that means observing them not just once, but again and again, watching for changes, shifts, and patterns that take millions of years to unfold. That's hard. It requires patience. It requires funding. And most of all, it requires imagination. Because studying galaxies is not just about recording data. It's about building stories out of light, gas, and gravity. And here's another layer to consider. Blue compact dwarf galaxies might help explain something much bigger. For a long time, astronomers have been trying to solve the mystery of how large galaxies like our own formed in the early universe. The standard theory says they were built through a process of merging smaller galaxies. But which smaller galaxies? Where did they come from? How did they behave? BCDGs might be part of that answer. They could be the leftover pieces of that cosmic construction process, the bricks that didn't get used, the fragments that stayed behind. Or maybe they're the ancient cores of galaxies that never grew. Either way, they carry clues about how galaxies assemble, how mass moves across the universe, and how structure evolves from chaos. Let's also talk about isolation. Some BCDGs are completely alone in space. They're not part of a cluster. They're not orbiting a bigger galaxy. They're just floating, isolated in the vast emptiness of space. That isolation raises even more questions. How did they form out there? What kind of conditions lead to a galaxy forming in the middle of nowhere? It suggests that under the right circumstances, galaxies don't need neighbors or collisions to become active. They can evolve on their own, driven by internal processes, or maybe even by dark matter structures we can't detect yet. Dark matter is another piece of this puzzle. Every galaxy we've studied, including BCDGs, seems to be embedded in a halo of dark matter. But because BCDGs are small and relatively simple, they might be some of the best places to study how dark matter behaves. Think of them as cosmic test labs. Less noise, fewer complications. That makes them perfect candidates for figuring out what dark matter actually is, how it clusters, and how it influences the behavior of normal matter like stars and gas. In fact, some researchers believe that BCDGs wouldn't be able to hold themselves together without the gravitational glue of dark matter. Their starbursts are so violent they should blow apart the galaxy. But something is holding them in place. Something invisible. Something strong. And dark matter is the best candidate we've got. Now, let's zoom out for a second. The universe is full of patterns, spiral arms, elliptical clusters, cosmic filaments. Everything seems to have a shape or structure. But BCDGs? They're wild cards. They're irregular. They're messy. They break the pattern. And sometimes, breaking the pattern tells you more than following it. These galaxies remind us that the universe isn't a machine. It's not a perfect system with everything in its right place. It's alive. It's strange. It has exceptions, outliers, and anomalies. And those are often where the biggest discoveries hide. So why don't we hear more about them? Why aren't BCDGs as famous as black holes, supernovae, or quasars? Probably because they don't have a flashy headline. They're not exploding or collapsing or bending time. They're just doing their thing. Quietly. Steadily. But that's exactly why they matter. They're not just snapshots of extreme events. They're slow-burn mysteries. They offer insights not from drama, but from endurance. From subtlety. From surviving through cosmic chaos. And maybe that's the biggest reason we need to pay attention to them. In a universe filled with giants and explosions, sometimes it's the smallest and quietest things that hold the deepest secrets. And again, across years and decades, building a kind of time-lapse of galactic behavior. This is already starting to happen. Astronomers are returning to the same BCDGs they studied 10 or 20 years ago and comparing the data. In some cases, they're seeing changes, new clusters forming, old ones fading, regions that were calm becoming active again. It's a slow, patient kind of science, but it's beginning to show us that BCDGs aren't frozen in time. They're dynamic. They live and change and react to their environments, just like larger galaxies do. And what makes this even more fascinating is that BCDGs are often found in areas of space that aren't very crowded. You might think that isolated galaxies would be boring, with nothing around to disturb them or trigger changes. But BCDGs prove the opposite. Even out there, in the quiet parts of the universe, wild things can happen. Starbursts can erupt. Gas can collapse. Supernovae can explode. It's like finding a rave in the middle of a desert. It's not what you expect, and that's exactly why it matters. These galaxies don't need external drama to become interesting. Their own internal chaos is more than enough. Some researchers believe that many BCDGs are fueled by cold gas accretion from the cosmic web, the vast network of dark matter and gas filaments that connect galaxies across the universe. If that's true, then these galaxies might not even need mergers to spark activity. They could be quietly sipping fresh gas from their surroundings, using that fuel to light up again and again. That would make them some of the purest examples of self-sustained star formation in the cosmos. And it would mean that our understanding of how galaxies grow, how they feed, how they evolve, needs to expand beyond just collisions and interactions. Let's also not forget how important BCDGs are for understanding dark matter. These galaxies are small, but they rotate in ways that don't make sense based on their visible mass alone. That means they must contain a lot of hidden mass, just like bigger galaxies do. And because they're simpler systems, they might actually be better places to study dark matter than large spirals like the Milky Way. There are fewer moving parts, fewer variables, so the signal is cleaner. That's why scientists are pointing sensitive instruments at BCDGs, measuring their rotation curves, trying to map where the invisible matter is hiding. If we can unlock that, we get one step closer to solving one of the biggest mysteries in all of physics. And yet, despite everything we know, and everything we suspect, BCDGs still manage to keep us guessing. Some of them have bizarre features, like off-center starbursts, or lopsided gas distributions, or strange companion clouds that don't seem to belong. Others flicker on and off in a way that's hard to explain. They're not behaving randomly, but they're not predictable either. It's like each one is following its own internal logic, its own rhythm. Some astronomers have even proposed that there might be different subtypes of BCDGs, each with their own origin story and path through the universe. All of this makes you realize something big. Space isn't just a cold, silent void dotted with stars. It's alive. It's active. And it's weird, so much weirder than we give it credit for. Blue Compact Dwarf Galaxies are a perfect example of that weirdness. They're small, chaotic, misunderstood, and full of potential. They don't just expand our understanding of galaxies, they explode it. They challenge our categories. They bend our rules. They whisper that the universe has secrets we haven't even thought to ask about yet. And that, more than anything, is why they matter. Those secrets in BCDGs, it might bring us closer to understanding what dark matter actually is. And that's no small thing. Dark matter is one of the biggest unsolved puzzles in all of science. It's everywhere, it's powerful, and yet we can't see it, touch it, or detect it directly. But we can observe its effects. We can watch how galaxies move, and how gravity behaves in ways it shouldn't, unless something invisible is adding mass to the system. Blue Compact Dwarf Galaxies, with their small sizes and exaggerated responses to dark matter, might just be some of the best test labs we have for probing this cosmic mystery. And that's wild, because no one expected that the tiniest galaxies could hold some of the biggest answers. Another strange thing about BCDGs is how some of them seem to defy even their own category. There are extremely metalpoor BCDGs that are so lacking in elements heavier than helium, it's like they were frozen in time shortly after the Big Bang. In the early universe, galaxies hadn't yet had time to build up metals through repeated star births and deaths. So finding galaxies today that are still that primitive is shocking. It's like discovering a living dinosaur in your backyard. These metalpoor BCDGs show us what the first galaxies may have looked like, and that's priceless. Because we can't travel back in time, these rare objects act like portals into the past, fossils that are still breathing. And it gets deeper. Some BCDGs are now believed to be among the first galaxies ever formed. We're talking about structures that may have started taking shape less than 1 billion years after the Big Bang. That means they've been around for nearly the entire age of the universe, quietly existing, evolving in strange, slow ways. They didn't get swallowed up by bigger galaxies. They weren't torn apart by gravitational forces. They just hung on. Survived. And now, billions of years later, they're still glowing with youthful energy, bursting with blue stars like they were just born. That kind of longevity paired with activity is unheard of in most galactic types. It makes you wonder how much more is out there, waiting to be seen, quietly defying every rule we think we've written. Let's talk about their shape for a second. BCDGs don't have the kind of structure you might expect. They're not spiral like the Milky Way, and they're not elliptical like old, red galaxies. They're often irregular, blobby, clumpy, uneven. That messiness is part of what makes them so unique. It's not because they're broken. It's because they haven't had time, or maybe they haven't had the right environment, to settle into a tidy form. And maybe that's a good thing. Because that raw, chaotic appearance is a sign of intense activity inside. It's like looking at a pot of water right as it starts to boil. Bubbles rising unpredictably, motion everywhere. That's what these galaxies are like. Chaotic, unstable, full of fire. They don't look elegant, but they're doing something extraordinary. They're forming stars in places where you wouldn't expect it to be possible. And they're doing it fast. This star formation isn't just occasional. In some BCDGs, it's happening in concentrated bursts that are 10, 20, even 100 times more intense than what we see in galaxies like our own. These bursts don't last forever. They usually burn out in a few million years, but during that time, they completely change the galaxy. New stars flood the system with light and radiation. Winds from young stars and supernova explosions push gas around, carving out cavities, triggering new waves of star birth. The whole thing becomes a cycle of destruction and renewal. And that cycle might be one of the keys to understanding how galaxies evolve over cosmic time. Even the stars themselves are different. In many BCDGs, you'll find what are called population 3-like stars, extremely hot, massive, and short-lived. These stars are thought to be similar to the first stars that ever existed. We've never directly observed a true population 3 star, because they all died out billions of years ago. But studying the extreme conditions in BCDGs might bring us closer than ever before. In a way, these galaxies are not just analogs for early universe conditions, they're living laboratories that let us test theories we could only simulate before. They offer us a window into an age we've never seen, and possibly never will again. And there's something poetic about that. These tiny, chaotic galaxies, ignored by many for years, are now seen as keys to the universe's origin story. They're not the biggest, not the brightest, not the most famous. But they might be the most honest. They haven't changed much. They haven't been altered by billions of years of mergers or stripped bare by tidal forces. They're pure, raw, and full of secrets. And if we're smart, we'll keep watching them. Because they're not just weird little galaxies floating out in the dark. They're messages from the beginning of time. Most older galaxies either. Instead, their shapes are irregular. Some look like blobs, others like cosmic clouds with no clear center. This chaotic structure isn't just about appearances. It tells us something deeper about their history. A spiral galaxy needs time and stability to form those beautiful, swirling arms. It needs to settle into a routine. But BCDGs are all about disruption. Their shapes reflect a life of turmoil, where gravitational forces, bursts of new stars, and explosive events constantly reshuffle the way the galaxy looks and moves. In many cases, a BCDG might have started to form a structure, only for a new wave of star formation to erupt and scramble everything again. It's like a city that keeps getting rebuilt every time it starts to take shape. Another key detail that makes BCDGs fascinating is their star populations. When you look at a BCDG through powerful telescopes, you're not just seeing one type of star. You're seeing layers of history. Some stars are just a few million years old, bright, blue, and burning fast. Others are billions of years old, dim, red, and barely hanging on. That contrast gives researchers a timeline of activity. By studying the color and brightness of these stars, astronomers can reconstruct the star formation history of the galaxy. They can see when it was most active, when it quieted down, and when it burst back into life. In this way, a BCDG is like a diary written in starlight, with every entry offering a clue to its past. What's even more compelling is how BCDGs challenge our definitions of what a galaxy is supposed to be. In school, we often learn that galaxies are massive collections of stars, gas, and dust, organized into familiar shapes and evolving in somewhat predictable ways. But BCDGs tear that idea apart. They're small, messy, and often completely unpredictable. They defy categorization. Some scientists have even debated whether certain BCDGs are actually galaxies at all, or if they're something else, perhaps the remnants of failed galaxies, or even proto-galaxies that never finished forming. This ambiguity is what makes them so interesting. They force us to think harder about the labels we use and the assumptions we make. They remind us that the universe doesn't care about fitting into neat categories. And then there's the mystery of their origins. Where do BCDGs actually come from? Some theories suggest they're the stripped-down cores of larger galaxies that got torn apart in collisions. Others think they may be newborn galaxies that are only just now coming to life, fueled by fresh gas drawn in from the cosmic web. There are even ideas that some BCDGs formed in complete isolation, in pockets of the universe that never experienced the same kind of chaotic growth as more populated regions. Each possibility paints a different picture of cosmic evolution. If we can figure out where BCDGs come from, we'll understand not just them, but the broader story of how the universe built itself from the ground up. In recent years, BCDGs have also become important targets for studying galactic winds, streams of gas and particles that are blasted out of galaxies by supernovae and intense star formation. These winds can push material out into intergalactic space, shaping the environment around a galaxy, and even influencing how other nearby galaxies evolve. In massive galaxies, these winds can be hard to study because of all the noise and complexity. But in BCDGs, where everything is stripped down and raw, the effects are easier to isolate. Scientists can track how the gas moves, how fast it's traveling, and what kind of elements it's carrying. It's like watching a fire up close instead of from a distance. And that kind of detailed observation can help refine our models of how galaxies grow, live, and eventually die. While others argue they're independent structures, born small and destined to stay that way. The truth is, we don't really know. And that uncertainty adds another layer of intrigue. If BCDGs are remnants of larger galaxies, that would suggest they carry within them the ashes of galactic destruction, a kind of cosmic memory of violent mergers and gravitational chaos. But if they've always been small, they may be survivors from a time when the universe was far less structured. That would make them some of the most ancient, untouched building blocks of everything else we see in space today. In both cases, their existence tells us something fundamental about how galaxies form, evolve, and interact over billions of years. Even more puzzling is how BCDGs manage to sustain multiple bursts of star formation without running out of fuel. In most galaxies, intense star formation is a temporary phase. The gas needed to create new stars eventually gets used up or blown away by powerful supernova explosions. But BCDGs seem to defy that rule. Some of them have been caught undergoing repeated bursts of star formation, as if they're somehow able to hold on to their gas or even draw in more from their surroundings. It's like watching a match relight itself after burning out. Scientists think part of the answer might lie in how isolated many BCDGs are. With fewer nearby galaxies to steal their gas or disrupt their structure, they might have a better chance at holding on to their resources over the long haul. But that doesn't explain everything. There's still something about their internal physics, something we don't yet fully grasp, that allows them to behave differently. And speaking of gas, one of the most striking things about BCDGs is how much of it they contain. For such small galaxies, they can have enormous reservoirs of hydrogen, the raw material for making stars. In some cases, the gas outweighs the stars themselves. That's completely backwards from what we see in most mature galaxies, where stars dominate the total mass. This abundance of gas might explain the recurring starbursts, but it also raises questions. Why hasn't all that gas already turned into stars? What's holding it back? One idea is that BCDGs have weaker gravitational fields, which makes it harder for gas to collapse into dense clouds that trigger star formation. Another possibility is that magnetic fields, cosmic rays, or turbulence inside the galaxy are keeping things stirred up just enough to prevent stars from forming all at once. Whatever the case, the result is a kind of slow-burning galaxy that keeps its star-making potential alive far longer than expected. And then there's the sheer beauty of it all. When astronomers look at BCDGs through telescopes like Hubble or James Webb, what they see is often breathtaking. These galaxies might be small, but they are glowing with color, brilliant blues from hot, young stars, mixed with reddish hues from older populations. Nebulae, clouds of gas and dust, light up with the energy of newborn stars, casting eerie glows across the surrounding space. It's like a fireworks show frozen in time. And even though they're often overlooked in favor of larger, more dramatic galaxies, BCDGs have a kind of raw, untamed beauty that sets them apart. They're not polished. They're not symmetrical. But they're alive with energy, motion, and mystery. And sometimes, that chaotic beauty tells us more about the universe than the most organized structures ever could. BCDGs are also helping astronomers test ideas about the early universe. Because some of them are so chemically primitive and so actively forming stars, they serve as analogs for what galaxies might have looked like shortly after the Big Bang. Scientists use detailed observations of BCDGs to build and refine models of early galaxy formation. They want to know what conditions are needed to trigger the first stars, how galaxies collect and hold onto gas, and how feedback from stars and supernovae affects further growth. By comparing real-world BCDGs with computer simulations of the early cosmos, researchers can see what's working and what's not. And sometimes, the differences between models and observations lead to entirely new theories about how galaxies work. There's also a fascinating connection between BCDGs and cosmic reionization, the period in the early universe when the first stars and galaxies turned on and reionized the hydrogen gas that filled space. This was a critical turning point in cosmic history, because it made the universe transparent to light and allowed structures like galaxies to become visible. Scientists believe that small, starbursting galaxies like BCDGs played a major role in this process. Even though they're tiny, their intense star formation can produce huge amounts of ultraviolet radiation. When you multiply that by millions of these kinds of galaxies scattered across the early universe, you end up with enough energy to reionize everything. That means understanding BCDGs could help explain one of the most important transitions in the universe's history. Even the locations of BCDGs can be unusual. Some are found floating alone in the void, far from any major galaxy clusters. Others are tucked into the outskirts of larger systems, like satellites that never quite got absorbed. Their isolation is often part of what makes them so unique. Without the constant tug-of-war from nearby galaxies, they can evolve in strange, unpredictable ways. They can hang on to gas, avoid violent mergers, and sustain star formation far longer than galaxies in busier environments. But sometimes it's the opposite. A close encounter with another galaxy can trigger a starburst in a BCDG, jolting it into action after billions of years of dormancy. These interactions, subtle or dramatic, can completely change the life path of a galaxy. And because BCDGs are so reactive, they can teach us a lot about how external forces shape galactic evolution. Surprising us. These galaxies don't rush through their lives. They move in fits and starts, experiencing bursts of creation separated by long stretches of relative calm. That stop-and-go pattern makes them feel almost alive, like they're reacting to unseen forces around them. And in a way, they are. Their star formation history is shaped not just by what's inside them, but by what's happening all around them in the wider universe. Nearby galaxies, dark matter halos, even the invisible threads of gas that weave between galaxies in the cosmic web, all of it plays a role in how a BCDG lives and changes over time. Now, one thing that keeps astronomers glued to their instruments is the fact that BCDGs are often found in the outskirts of galaxy clusters or even in complete isolation. This is important, because location tells us a lot about a galaxy's life. Galaxies in the center of clusters are usually massive, mature, and shaped by constant interactions with their neighbors. But BCDGs often live on the margins, away from the chaos, almost like cosmic introverts. And this isolation might actually protect them. Without other galaxies constantly pulling on them or stealing their gas, BCDGs might be able to preserve their primitive structure and composition for much longer. That makes them especially valuable to researchers. In a way, studying BCDGs is like digging up fossils in a part of Earth where time has stood still. These galaxies may be holding on to clues about the early universe that we can't find anywhere else. But here's where things get even more mysterious. Some BCDGs don't stay small forever. Every once in a while, we catch one in the act of merging with another small galaxy or absorbing a nearby gas cloud. And when that happens, something wild can unfold. The influx of new material acts like fuel thrown onto a fire, triggering massive waves of star formation. The whole galaxy lights up, becoming brighter and more chaotic. And in some cases, these mergers might eventually create something new entirely, a larger galaxy with a different structure and identity. So what we're seeing with BCDGs might not be their final form. They could be temporary phases in a longer transformation. Like caterpillars before the cocoon, or sparks before a blaze. They remind us that in the cosmos, nothing stays the same forever, and even the smallest structures can evolve into something massive and complex given enough time. And while we're talking about evolution, we can't ignore how BCDGs are helping us understand the early universe. Their low metallicity, the lack of heavy elements, makes them similar to the first galaxies that ever formed. Heavy elements like carbon, oxygen, and iron are created in stars and spread throughout galaxies when those stars explode. So the more generations of stars a galaxy has, the more metals it contains. But BCDGs often have very little of these elements, which means they haven't been through many star cycles yet. That's exactly what we expect in galaxies that formed shortly after the Big Bang. So when we study BCDGs, we're basically looking at time capsules, modern snapshots of ancient conditions. And that's why some scientists believe BCDGs are the closest thing we have to direct evidence of what the universe looked like in its early years. By analyzing their gas, stars, and structure, we can test theories about how the first galaxies formed, what kinds of stars they made, and how they eventually evolved into the complex systems we see today. It's like holding a missing piece of a cosmic puzzle, one that might finally help us understand how the chaotic fireball of the Big Bang gave rise to the beautiful, structured universe we now explore. Universe. See, one of the biggest challenges in modern astronomy is figuring out what galaxies looked like right after the Big Bang. That period is so far away in time and space that even our best telescopes struggle to see it clearly. The light from those early galaxies has been stretched and dimmed by billions of years of cosmic expansion. But blue compact dwarf galaxies give us a kind of shortcut. Because they're small, metal-poor, and actively forming stars, just like the galaxies that existed shortly after the universe was born, they act as living analogs to that early era. Studying them is like having a time machine that doesn't require looking 13 billion light-years away. It's one of the few ways we can get real, hands-on data about what conditions might have been like in the first few 100 million years of the universe. And here's where things get wild. Some BCDGs have metallicity so low, they're practically pristine. That means the gas inside them has barely been polluted by previous generations of stars. In cosmic terms, that's rare. Most galaxies have gone through so many cycles of star formation and destruction that their gas is loaded with heavy elements, stuff like carbon, oxygen, and iron, all forged in the hearts of stars. But BCDGs? Some of them still contain gas that's 99% hydrogen and helium, just like what came out of the Big Bang. That's a big deal, because it allows scientists to study how stars form and evolve in conditions that are almost identical to the early universe. These galaxies are cosmic laboratories, letting us recreate experiments that happened before Earth even existed. Now, what's even more mind-blowing is that BCDGs aren't just interesting because of what they are, they're also mysterious because of what they're not. They're not spiral galaxies. They're not elliptical galaxies. They don't follow the neat categories we like to use when organizing the universe. Their shapes are irregular. Their motions are chaotic. Their star populations are wildly uneven. It's as if they refuse to play by the rules. And that breaks our models. When scientists try to plug BCDG data into simulations of galaxy formation, things start to fall apart. The math doesn't add up. The predictions don't match the observations. And that's a red flag. In science, when something doesn't fit, it usually means you're about to discover something new. And then there's the question of how many BCDGs are actually out there. You'd think that in a universe with trillions of galaxies, small ones would be easy to spot. But they're not. Most BCDGs are faint, tucked away in remote parts of the sky, and easy to miss unless you're looking in just the right place with the right instruments. This means we're probably undercounting them. There could be millions more, quietly glowing in the dark, waiting to be found. And each one could be a treasure trove of information about galaxy evolution, star formation, cosmic chemistry, and even dark matter. Because let's not forget that dark matter probably plays a huge role in shaping BCDGs, even though we can't see it. These galaxies may be held together not just by their stars and gas, but by invisible halos of dark matter wrapping around them like scaffolding. If we can figure out how that dark matter behaves in BCDGs, it could give us huge insights into one of the biggest mysteries in the universe. But despite everything we've learned, BCDGs are still full of unanswered questions. Why do some of them suddenly flare up with new stars while others stay quiet? What triggers their starbursts, and why are they so intense compared to larger galaxies? How do these tiny systems retain their gas over billions of years? And why are they so chemically simple when the rest of the universe is constantly becoming more complex? These aren't just technical details, they're fundamental puzzles. Because if we can solve them, we might unlock new understanding about how the universe works on its most basic level. And that's the heart of the mystery. BCDGs look small and unimportant, but they might hold the keys to everything. Might think we've found most of them already, considering how far our telescopes can see. But here's the truth, we've probably only scratched the surface. Blue compact dwarf galaxies are faint, small, and easily overlooked, especially when they're located far from brighter, more obvious structures in the universe. Some might be hiding behind or beside larger galaxies. Others might be cloaked in dust or buried in the noise of deep space observations. And since they often don't emit strong radio signals or have defined shapes, many of them don't stand out in sky surveys. That means there could be thousands, or even millions, of these tiny galaxies scattered across the universe that we simply haven't noticed yet. They could be orbiting bigger galaxies like cosmic satellites, or drifting through intergalactic space, isolated and quiet. And every one of them could hold a piece of the universe's missing story. Even more fascinating is the idea that blue compact dwarf galaxies might be relics of the first galaxies that ever formed. Right after the Big Bang, the universe was filled with nothing but hydrogen and helium. No stars. No planets. No heavy elements. Just pure, unprocessed gas. Slowly, tiny clumps of this gas began to collapse under gravity, igniting the first stars and forming the first galaxies. But those early galaxies weren't grand spirals or massive clusters. They were more like today's BCDGs, small, chaotic, and packed with young, hot stars. Some astronomers believe that certain BCDGs we see today may be direct descendants of those ancient structures. If that's true, then observing them could be the closest thing we have to watching the birth of galaxies in real time. It's like having access to a fossil that's still breathing, still burning, still alive. But there's a twist to this story, and it lies in the nature of dark matter. Every galaxy we've ever studied, big or small, seems to be held together by a mysterious, invisible substance called dark matter. We don't know exactly what it is, but we know it's out there because of the way galaxies spin and move. Without it, they'd fall apart. BCDGs are no exception. Despite their small size, they seem to have a disproportionately large amount of dark matter. That's strange. Why would such tiny galaxies be so heavily influenced by something we can't even see? Some theories suggest that BCDGs are actually dominated by dark matter halos, with just a sprinkling of visible stars and gas in the center. If true, that would make them perfect test subjects for studying dark matter directly. They're small enough that we can isolate their gravitational behavior, but large enough to give us meaningful data. They're like clean test tubes in a cosmic lab, offering insight into one of the universe's greatest mysteries. What's more, their starbursts might be telling us something about how galaxies ignite. In normal galaxies, star formation tends to be steady and spread out. But in BCDGs, stars form in intense bursts, clustered in small regions, and sometimes triggered by collisions with gas clouds or even other dwarf galaxies. These starbursts can produce huge amounts of radiation, blowing winds that push gas out of the galaxy entirely. That makes BCDGs fragile. A single starburst might be enough to shut down star formation permanently, leaving behind a lifeless husk. But not always. Sometimes, these galaxies recover. They pull in more gas. They start forming stars again. And the cycle continues. It's a delicate balance. One push too hard and the galaxy dies, but just enough, and it thrives. That kind of volatility is rare in the universe. Most big galaxies are stable. But BCDGs? They're on the edge, always changing, always at risk of tipping into chaos. And that makes them thrilling to study. Of visible stars and gas at their centers. That would make them some of the most dark matter-dense objects in the universe. And if that's true, then understanding how BCDGs form, evolve, and survive could be a direct path to unlocking the secrets of dark matter itself. Think about that. These tiny, overlooked galaxies could be the key to understanding the most mysterious ingredient in the entire cosmos. The stuff that makes up most of the mass in the universe. The stuff that doesn't emit light, doesn't interact with normal matter, but bends gravity and sculpts the large-scale structure of the universe. And these galaxies, these odd, flickering beacons in deep space, might be our best shot at cracking that code. Another layer to the mystery is how BCDGs manage to survive. The universe is a violent place. Galaxies collide, black holes grow and swallow, massive stars explode with enough force to tear apart entire star systems. In that chaos, how do these fragile, small galaxies persist? Some theories say they survive precisely because they're small. They don't have the gravitational pull to attract much attention from bigger galaxies. Others suggest that they're tough in ways we don't yet understand. They might be protected by their dense dark matter cores, or maybe their low metallicity makes them less prone to the destructive feedback loops that plague more evolved galaxies. And then there's the possibility that they're constantly being born, living short, bright lives, and then fading into obscurity before we can even notice. Either way, their survival is a question we haven't fully answered. Now let's talk about starburst activity, one of the most intense and defining traits of blue compact dwarf galaxies. These galaxies don't just form stars, they explode with star formation. It's like someone flipped a switch and suddenly, entire regions of gas collapse into clusters of new stars, all at once. This rapid star formation creates immense amounts of radiation, stellar winds, and supernova explosions. In a bigger galaxy, that kind of activity might go unnoticed. But in a tiny galaxy like a BCDG, it's enough to rip the place apart. And yet it doesn't. Somehow, these galaxies endure these violent episodes again and again. That raises questions about their internal structure, their gas recycling processes, and how they regulate star formation over time. What's triggering these bursts? Are they interacting with other galaxies? Are they absorbing pristine gas from intergalactic space? Are they part of a hidden cycle we haven't yet discovered? Some astronomers have proposed that these galaxies aren't isolated at all, that their starbursts are caused by collisions or close encounters with other, unseen galaxies. When two galaxies pass close to each other, their gravitational forces can pull and twist the gas inside them, triggering waves of star formation. If BCDGs are doing this regularly, it would suggest a much more interactive and dynamic universe at small scales than we previously thought. And if they're not interacting with other galaxies, then maybe they're tapping into something else, some reservoir of cold gas, hidden in the void, waiting to be turned into stars. That idea has gained traction recently, as more sensitive instruments detect hints of diffuse gas clouds surrounding some dwarf galaxies. Maybe BCDGs are the visible tip of a much larger, invisible iceberg. We also have to talk about their colors. These galaxies are called blue for a reason. That blue hue comes from the massive stars inside them, stars that are burning hot and fast, pouring out ultraviolet radiation. But the color isn't just cosmetic. It tells us a lot about what's happening inside. Blue light means youth. It means activity. It means change. Unlike redder galaxies, which are older and more stable, blue galaxies are caught in the act of transformation. They're still evolving. Still growing. Still reacting to the forces around them. That makes them unpredictable. You might observe a BCDG today and see it bursting with light, only to return a few million years later and find it dark, calm, and nearly invisible. These galaxies live in cycles, and we're only just starting to map those cycles out. And that brings us to another point: how BCDGs evolve over time. Do they eventually become something else? Do they grow into larger, more structured galaxies? Or do they fade away, consumed by their own starbursts and stripped of gas? Some researchers believe that BCDGs are a kind of transitional phase, a step between primordial gas clouds and mature galaxies. Others think they're evolutionary dead ends, destined to flare up and burn out without ever achieving long-term stability. There's also the theory that they might be the building blocks of larger galaxies, that in the early universe, countless BCDGs merged together, forming the first spiral and elliptical galaxies we see today. If that's the case, then understanding BCDGs isn't just about studying the past, it's about understanding how everything we see around us came to be. And here's something even weirder: some BCDGs might not be natural at all. There's a fringe theory floating around in the astrophysics community that suggests some of these galaxies could be artificially manipulated. Not in the sense of being built from scratch, but in the sense that some advanced civilization could be steering their evolution, harvesting stars, managing gas flows, or experimenting with starburst mechanics. Now, this isn't a mainstream idea, and there's no concrete evidence for it. But it's part of a larger conversation about how we might detect alien intelligence in ways that don't involve radio signals or giant antennas. Maybe the best place to look for signs of intelligent life isn't in messages, it's in anomalies. Things that don't fit. Things like Blue Compact Dwarf Galaxies. That keeps repeating over billions of years? The answers to these questions aren't fully known, and that's exactly what makes BCDGs so fascinating. They challenge our understanding of how galaxies are supposed to behave. They don't follow the usual rules. They're small yet intense. Old yet active. Isolated yet somehow still changing. It's as if each BCDG is operating on its own script, outside the typical patterns we've come to expect from the rest of the universe. Another major puzzle is their chemical composition. In most galaxies, older generations of stars have gone through cycles of life and death, producing heavier elements like carbon, oxygen, and iron, which then enrich the surrounding gas. This process, called metal enrichment, gradually increases the metallicity of the galaxy over time. But in many BCDGs, the metallicity is shockingly low. It's almost as if they haven't been through that many cycles of star birth and death at all. This has led some researchers to argue that certain BCDGs might be genuinely young galaxies, just now forming their first generations of stars. But that idea creates a paradox. How could galaxies still be forming for the first time in a universe that's nearly 14 billion years old? Shouldn't all the raw material have already been used up? Unless these galaxies are somehow tapping into untouched reservoirs of primordial gas, left over from the Big Bang, that are still drifting through space. If that's the case, then studying BCDGs might give us a window into the conditions of the early universe in ways we've never had before. Then there's the mystery of their structure. Unlike grand spirals or massive elliptical galaxies, BCDGs are often irregular and chaotic. They don't have the symmetry or organization that we usually associate with galactic architecture. Some look like blobs. Others resemble fireworks frozen in time. Some are so compact and small that they almost look like oversized star clusters. And yet, despite their strange appearances, many of them manage to stay gravitationally bound and stable. That raises big questions about how galaxies form structure in the first place. What forces are shaping these galaxies? What prevents them from flying apart during intense starbursts? Could their irregular shapes be a clue that we're missing something fundamental about the way gravity, gas, and energy interact on small scales? Let's not forget about the role of gas, specifically hydrogen gas, which is the primary fuel for star formation. BCDGs tend to have a lot of it. In some cases, more than half the mass of the galaxy is made up of neutral hydrogen. That's unusual. Most galaxies, especially ones undergoing active star formation, tend to burn through their gas quickly. But BCDGs often seem to retain large reservoirs of gas, even during starburst phases. Why? Some researchers think it has to do with the way gas is distributed within the galaxy. Others suspect that the star formation in BCDGs might be surprisingly inefficient, meaning they don't convert gas into stars as effectively as larger galaxies do. That could be because of feedback from young stars, or maybe because of turbulence in the gas itself. Either way, this abundance of hydrogen is one of the key reasons BCDGs are so valuable to astronomers. They act like laboratories where we can study how stars form from raw material in low metallicity environments, something that's hard to do in our own galaxy, where the gas is already heavily processed and enriched with metals. And there's more. Some of the most distant BCDGs we've observed show characteristics that link them to ancient, high-redshift galaxies that existed just a few billion years after the Big Bang. In other words, BCDGs might be modern analogs of those ancient systems. They're small, faint, metal-poor, and bursting with star formation, just like the first galaxies we believe existed in the early universe. That means we can use nearby BCDGs to test theories about galaxy formation in the early universe, without needing to rely solely on observations of faint, distant objects that are hard to study. It's like having a time machine sitting right in our cosmic backyard. By analyzing these nearby relics, we can rewind the clock and see how the earliest galaxies might have behaved, evolved, and eventually merged to form the more complex systems we see today. They are often found to be loaded with neutral hydrogen, far more than you'd expect given their size. It's like they're hoarding the raw material for making stars, keeping vast reserves tucked away in clouds that stretch far beyond their visible light. This massive reservoir of hydrogen is one of the main reasons why they can keep igniting new starbursts even though they're small. But it also raises a question: why hasn't all that gas been used up already? In bigger galaxies, intense star formation usually leads to feedback processes that blow away or heat up the gas, making it harder for more stars to form. But BCDGs seem to keep going, like a fire that never runs out of wood. Some scientists believe that their low metallicity might be the key. Without heavy elements to trap heat, the gas cools more efficiently, allowing it to collapse and form stars again and again. That means these galaxies might have found a way to bypass the normal limits of star formation, giving them a kind of long-term sustainability that most galaxies don't have. And that opens up even more questions. Could blue compact dwarf galaxies represent a kind of second chance galaxy? Objects that are only now waking up in a universe that's already mature? If so, what triggered that awakening? Was it a gravitational interaction with a nearby galaxy that stirred up their gas and jump-started star formation? Or did they just slowly accumulate cold gas over billions of years until they reached a tipping point? Some researchers have proposed that these galaxies might be surrounded by massive, invisible halos of dark matter that protect them from external disturbances and help them retain gas. That would explain their longevity, and why they seem so isolated. But again, this is a theory that needs more evidence, and the answers are still out there, drifting somewhere in deep space, waiting to be found. Another intriguing layer to this mystery is the possibility that BCDGs could be analogs for the very first galaxies in the universe. Because they are low in metals and rich in gas, they resemble the conditions that astronomers believe were common in the early universe. That means by studying these galaxies, we might be peering backward in time, getting a rare look at what galaxy formation looked like just a few 100 million years after the Big Bang. But here's the twist: BCDGs are nearby, relatively speaking. They're not buried deep in the early universe, requiring massive telescopes like the James Webb to observe. They're accessible. We can study them up close. And that makes them priceless scientific tools. If we can understand how star formation, chemical evolution, and feedback processes work in BCDGs, we might finally be able to map out the steps that took us from a dark, gas-filled early universe to the vibrant, starlit cosmos we see today. Yet, despite everything we know, or think we know, there's still so much about these galaxies that doesn't make sense. For example, why do some BCDGs seem to flare up with sudden starbursts while others remain quiet for millions of years? What controls the timing? Is there a hidden clock ticking inside them, or are their bursts completely random? Why are some of them surrounded by faint tidal tails and streams of gas, hinting at past collisions, while others seem untouched? Are we seeing different evolutionary stages, or are there entirely different types of BCDGs that just happen to look similar? Some may have been satellites of bigger galaxies that were stripped and left behind, while others may have formed completely in isolation. And still others might be fragments from ancient collisions, still burning with leftover energy. The variety is huge, and the explanations are far from settled. Let's go even deeper. In recent years, astronomers using powerful telescopes and surveys have discovered that some BCDGs host superstar clusters, massive groups of young, hot stars packed tightly into small volumes. These clusters are among the most energetic places in the universe, filled with ultraviolet radiation, stellar winds, and frequent supernovae. And yet, somehow, they don't tear the galaxy apart. That's one of the biggest paradoxes. In theory, the feedback from these superclusters should heat up the gas, blow it out of the galaxy, and stop star formation cold. But that doesn't always happen. Instead, we see repeated cycles of starbursts, quiet periods, and then more starbursts. It's like these galaxies are operating in a loop that defies our standard models of galactic evolution. Maybe the gas doesn't escape entirely. It just gets pushed out and later falls back in. Or maybe these galaxies are pulling in fresh gas from the cosmic web, replacing what they lose. And then there's the question of their eventual fate. What happens to BCDGs over the long run? Do they burn out and fade away, becoming invisible relics floating in deep space? Or do they evolve into something else entirely, perhaps the cores of future galaxies, or the building blocks of new systems formed through mergers? Some theories suggest that BCDGs could eventually transform into dwarf elliptical galaxies once their gas is depleted and star formation stops. Others argue that they might become ultra-compact dwarfs, or even globular cluster-like remnants. But so far, we don't have a complete picture. Observing that transformation is almost impossible with human timescales, so we have to rely on simulations and indirect evidence. And maybe, just maybe, some of these galaxies hold secrets we haven't even considered yet. What if BCDGs are sites of exotic physics? What if the low metallicity environments allow strange particles or unknown processes to occur that don't happen in bigger, more complex galaxies? It sounds speculative, but science often starts with questions like these. Every time we peel back a layer, we find another one underneath. What seems like a small, obscure object at first glance could end up being the cornerstone of a new understanding of the universe. That's the power of looking where others aren't. Of paying attention to the quiet corners of space that most people ignore. Close, in far greater detail than the ancient galaxies at the edge of the observable universe. That gives astronomers a unique advantage, because while it's incredibly difficult to get precise measurements from galaxies that are billions of light years away, BCDGs are right in our cosmic backyard. We can examine their gas dynamics, measure their star formation rates, and analyze the chemical makeup of their stars with far greater accuracy. And through this process, we may be able to reconstruct a timeline of how galaxies formed in the early universe by comparing what we see in these nearby dwarfs to what we detect in the deep, ancient cosmos. This connection between the near and the far, between the now and the beginning, is one of the most powerful tools in cosmology, and BCDGs may just be the missing puzzle piece that ties it all together. Now, let's talk about starburst activity itself. One of the defining features of blue compact dwarf galaxies is that they undergo intense, short-lived periods of rapid star formation. During a starburst, these galaxies can produce stars at rates that rival much larger galaxies, despite their small size. It's like watching a firecracker explode in slow motion. The core of the galaxy becomes incredibly bright, filled with massive, hot, blue stars that outshine everything else. But here's the thing. These starbursts don't last. They flare up, and then they fade. Scientists are still trying to understand what triggers these bursts, how long they last, and what causes them to shut down. Some theories suggest that internal processes, like the buildup of dense gas in the center, might ignite these episodes. Others argue that external influences, such as interactions with nearby clouds of gas or minor galaxy mergers, might be the spark. But either way, the result is the same, a temporary explosion of light and energy that leaves a lasting impact on the galaxy's structure and evolution. What's especially curious is what happens after the starburst ends. You'd expect the galaxy to quiet down, maybe even fade into obscurity. But many BCDGs show signs of multiple starburst episodes, separated by millions, or even billions, of years. This cycle of activity suggests that something is allowing them to restart the process over and over again. Some researchers believe that the feedback from each burst, stellar winds, supernova explosions, and radiation pressure, temporarily halts star formation by heating and dispersing the gas. But over time, the gas cools and settles back down, eventually becoming dense enough to trigger another round of stars. If this is true, then BCDGs are living in a kind of loop, constantly switching between dormancy and ignition. That's a fascinating behavior, especially for galaxies that aren't part of any large cluster or interacting system. It hints at a delicate internal balance, a hidden rhythm governed by the slow dance of gravity and gas. Let's zoom in even closer, into the core of these galaxies, where the most intense activity happens. In the heart of a BCDG, you'll often find clusters of newly formed stars, many of them massive and short-lived. These stars burn incredibly hot, pouring out ultraviolet radiation that ionizes the surrounding gas and creates bright, glowing regions known as H2 regions. These are the same glowing nebulae we see in images of nearby star-forming areas, like the Orion Nebula, but in BCDGs, they can dominate the entire visible structure of the galaxy. And then there are the supernovae. As massive stars reach the end of their lives, they explode in titanic blasts that can outshine the entire galaxy for a brief moment. These explosions send shockwaves rippling through the surrounding gas, triggering new waves of star formation, or blowing gas away, depending on the energy involved. The interplay between creation and destruction is on full display in these environments, and it's incredibly dynamic. But not everything in a BCDG is violent. In fact, part of what makes them so compelling is the contrast between their chaotic cores and their relatively quiet outskirts. If you look at the outer regions of a typical BCDG, you'll often find faint, diffuse light, evidence of older stars that formed long before the current starburst. These outer halos suggest that many BCDGs aren't truly young, even if their cores look that way. Instead, they may have been around for billions of years, quietly evolving, until something triggered a new round of activity. This dual nature, young in the center, old on the edges, is another reason why they're so hard to classify. They don't fit neatly into the categories we usually use. They're not just dwarf galaxies. They're not just irregulars. They're hybrids, shapeshifters, cosmic chameleons. And that brings us to a deeper question. What do blue compact dwarf galaxies really tell us about the universe? At first glance, they might seem like oddities, small, weird galaxies that don't play by the rules. But in reality, they may be among the most important laboratories for understanding cosmic evolution. They offer a rare glimpse into processes that were common in the early universe but are now rare in our current epoch. They show us how galaxies form, how stars are born in extreme environments, and how feedback from those stars can shape the future of a galaxy. They also challenge our assumptions. We like to think of the universe as following predictable patterns. Spirals form this way, ellipticals form that way. But BCDGs remind us that nature doesn't always follow our rules. Sometimes it takes a detour. Sometimes it writes its own script. And speaking of scripts, the story of BCDGs is still being written. New discoveries are being made all the time, especially as more powerful telescopes come online. The James Webb Space Telescope, for example, is expected to shed new light on these enigmatic galaxies, allowing us to peer deeper into their structure and analyze their chemical composition with unprecedented detail. With tools like this, we may finally start to answer some of the big questions. Are BCDGs relics of the early universe? Are they still forming today? What role do they play in the broader ecosystem of galaxies? And perhaps most intriguingly, what can they teach us about our own cosmic origins? Of star formation. It's a fascinating cycle, almost like the galaxy is breathing. Inhale, exhale, flare up, quiet down, and repeat. This makes blue compact dwarf galaxies feel alive in a sense, going through rhythms of birth and rest that are hard to predict but undeniably real. And it also raises a bigger question: how many more galaxies out there are following similar hidden patterns, unnoticed because they're so small or faint? What if the cosmos is full of these flickering lights, quietly going through cycles of intense creation and dormancy while we focus only on the bigger, brighter systems? That brings us to an even deeper mystery. How isolated really are these galaxies? On the surface, BCDGs often appear to be floating alone in space, away from major clusters or larger galaxies. But when astronomers zoom in, things get more complicated. Some blue compact dwarfs have faint companions, streams of gas, or tails of stars that suggest past interactions. Others seem to sit at the edges of filaments in the cosmic web, maybe drawing in cold gas from the vast intergalactic medium. In fact, some of the most dramatic starbursts in these galaxies may have been triggered by invisible forces, small gravitational nudges, the infall of cold gas, or even the remnants of long-vanished companions. These invisible interactions could explain how a seemingly quiet, isolated dwarf suddenly erupts into a blazing starburst. It reminds us that the universe is never as still or simple as it looks. And here's another twist. When astronomers study the outer regions of these galaxies, they often find huge envelopes of gas that extend far beyond the visible stars. In some cases, the gas is spinning, forming faint rotating disks that hint at a much larger structure. In others, the gas seems chaotic, like it's been stirred up by past violence. Some galaxies even have multiple components, a compact, bright core surrounded by diffuse, irregular halos. These features suggest that what we see in visible light is just the tip of the iceberg. Beneath that surface, there's a complex, layered history written in gas and dark matter. It's like reading a book with most of the pages still invisible. We see the climax, the starburst, but we don't see the full build-up. And that missing context is what makes Blue Compact Dwarf Galaxies so irresistible to researchers. When it comes to the stars themselves, these galaxies are even more unique. Their stellar populations are dominated by young, hot, massive stars that burn blue and live short lives. But in some cases, astronomers have detected older stars hidden within the galaxies, suggesting that they aren't as new as their current appearance suggests. That's important, because it tells us that many BCDGs didn't just suddenly appear. They've existed quietly for billions of years, going through slow, intermittent phases of activity. This hidden older population gives us valuable clues about their origins. Some may have formed soon after the Big Bang, built up slowly over time, and only recently entered a new phase of star formation. Others might have formed from gas stripped from nearby galaxies, pulled together into new structures by gravitational forces. There isn't one clear origin story. It varies from one BCDG to another. And that variety is part of what makes studying them so challenging and exciting. But perhaps the most mind-bending idea is the role these galaxies might play in the grand story of the universe. Because of their simplicity and low metal content, they might be one of the closest living relatives of the first galaxies. That means they could hold the key to understanding how the universe transitioned from a dark, featureless expanse of hydrogen and helium into a complex web of stars, galaxies, and planets. By studying their chemical makeup, star formation rates, and gas dynamics, astronomers can refine their models of early galaxy formation. They can test theories about how the first stars lit up, how galaxies assembled, and how the cosmic environment evolved. Blue Compact Dwarf Galaxies may not look like much from afar, but they could contain answers to some of the biggest questions in cosmology. These stars are the reason the galaxies appear blue. They outshine the older, cooler stars that might also be present but are far less luminous. But here's the catch. Because these massive stars are so short-lived, the blue light we see is a kind of cosmic flash. It means we're witnessing something extremely temporary in galactic terms. In just a blink of an eye, astronomically speaking, the galaxy could shift back to a dim, red, quiet state, almost invisible to telescopes tuned to detect bright, hot stars. That makes every BCDG a sort of cosmic snapshot, a brief chapter in a much longer story that we're lucky to catch. And the more we look, the more it becomes clear that there may be countless dwarf galaxies out there that we're simply not seeing, either because they've already burned through their starburst phase or haven't yet entered it. What's even stranger is the metallicity of these galaxies. In astronomy, metals refer to all elements heavier than hydrogen and helium, so things like oxygen, carbon, and iron. These elements are created in stars and spread through galaxies by stellar winds and supernova explosions. So, typically older, more evolved galaxies are richer in metals. But blue compact dwarf galaxies often have extremely low metallicities. That suggests they haven't formed many generations of stars, or that much of their gas has remained relatively untouched since the early universe. In other words, they might still be made of the same pristine material that filled the cosmos shortly after the Big Bang. Studying that gas could give scientists a rare window into what the universe was like before stars and galaxies had time to significantly alter the chemical makeup of their surroundings. It's like finding a sealed bottle of ancient air and cracking it open to learn how Earth's atmosphere used to be, only on a cosmic scale. But these galaxies aren't just labs for the past, they're also places where we can test the future. That's because they challenge our models of how galaxies evolve. According to most simulations, small galaxies should have trouble holding onto their gas. Their weak gravity means that supernovae and stellar winds can blow material away, potentially shutting down star formation altogether. But BCDGs seem to defy that logic. Even after massive starbursts, they still retain huge amounts of gas. Somehow, they're either more efficient at keeping their material than expected, or they're constantly pulling in fresh gas from somewhere else. This resilience has forced scientists to rethink what they thought they knew about galaxy evolution, especially in low-mass environments where feedback should dominate. It raises big questions about how stars formed in the early universe when dwarf galaxies were much more common, and whether today's BCDGs are echoing those ancient times in ways we're only beginning to understand. Their dark matter profiles are equally puzzling. While dark matter can't be seen directly, we can infer its presence from the way stars and gas move inside a galaxy. And in many BCDGs, those motions suggest the presence of large amounts of dark matter. But sometimes, the rotation curves, the speed at which stars and gas orbit, don't match what we expect. In some cases, there's too much mass concentrated in the center. In others, the mass is spread out more evenly than models predict. This inconsistency has led to a flurry of new theories about the nature of dark matter itself. Maybe it's not as cold or slow-moving as we thought. Maybe it interacts with itself or with normal matter in ways we haven't accounted for. Or maybe our entire understanding of gravity needs to be updated at very small scales. Whatever the answer, blue compact dwarf galaxies are at the heart of the debate. They're acting like a cosmic laboratory where the rules we think we know are being bent, or broken, in ways that force us to go back to the drawing board. And then there's the question of how many of these galaxies are out there. Because BCDGs are so small and faint outside their starburst phases, they're notoriously difficult to find unless they're actively forming stars. That means we may only be seeing the tip of the iceberg, those galaxies that just happen to be on when we look. The rest could be dormant, waiting for a fresh wave of gas or some gravitational nudge to kickstart another burst. If that's true, the universe could be teeming with hidden dwarf galaxies, quietly floating between the larger, brighter galaxies we usually focus on. These invisible systems might account for a significant portion of the universe's baryonic matter, the normal matter made of atoms, and could be key to solving the mystery of the so-called missing baryons. We know the early universe had a certain amount of matter based on observations of the cosmic microwave background. But when we tally up all the galaxies, stars, and gas clouds we can see today, we come up short. Blue compact dwarf galaxies and their quieter cousins might be where that missing matter has been hiding all along. Even more intriguing is how these galaxies relate to the formation of larger galaxies. It's long been believed that massive galaxies grew over time by swallowing up smaller ones, a process known as hierarchical merging. If that's true, then BCDGs could be the surviving remnants of the original building blocks of cosmic structure. By studying them, we're essentially peering back at the raw ingredients of galactic evolution. Some of the stars in the Milky Way's halo may have originally formed in dwarf galaxies like these, torn apart and consumed by our own galaxy over billions of years. In that sense, understanding BCDGs isn't just about the galaxies themselves, it's about understanding our own cosmic ancestry. Where did the stars in our sky come from? What smaller systems came together to make the galaxies we see today? BCDGs might not have all the answers, but they hold crucial clues that are helping scientists fill in the blanks. And then we reach the cosmic timescale. These galaxies are small, yes, and fleeting in their brightest moments. But they exist on a timeline that stretches billions of years. The starbursts we observe today may be just one phase in a cycle that has repeated dozens of times. Between each burst, the galaxy cools, changes, and slowly builds toward the next. In this way, a BCDG isn't a one-hit wonder, It's more like a slow-burning star factory with periodic flare-ups. That's important because it changes how we think about galactic activity. We often focus on galaxies that are always active, always forming stars. But the BCDGs show us that even quiet, unassuming systems can surprise us, and that a galaxy's story is rarely over, even when it seems dormant. Some astronomers believe that blue compact dwarf galaxies may be actively feeding on gas from the intergalactic medium, the vast, thin stretches of hydrogen that exist between galaxies. This idea isn't just interesting, it's potentially revolutionary. If BCDGs can draw in fresh material from outside themselves, it means they have a direct connection to the cosmic web, the massive filamentary structure that links all matter in the universe. It suggests that rather than being isolated, dying remnants, these small galaxies could actually be part of a dynamic, ongoing cycle of growth and renewal. They may be tapping into the same processes that shaped the earliest galaxies, operating on smaller scales but governed by similar laws. In that way, they serve as test cases for our larger theories of cosmology. And because they're relatively nearby, compared to distant early galaxies, they offer a practical way to test those ideas using current instruments. Another strange feature of blue compact dwarf galaxies is their chaotic structure. Most galaxies have some kind of form: spirals with neatly arranged arms, ellipticals with smooth, rounded shapes. But BCDGs are often irregular, lumpy, and disordered. They lack symmetry. Their star-forming regions are spread out unevenly, and the galaxies themselves can appear misshapen or fragmented. That messiness may be a clue to how they evolve. It's possible that many of them are the result of mergers between even smaller dwarf galaxies. When two or more tiny galaxies collide, they can spark intense bursts of star formation and scramble the internal structure, leaving behind the kind of disorder we observe in BCDGs. This makes them excellent laboratories for studying galactic interactions on the smallest scales, events that might mirror, in miniature, the much larger mergers that shape the massive galaxies we see today. The environments of these galaxies also raise interesting questions. Blue compact dwarf galaxies tend to be found in relative isolation, far from the crowded clusters where larger galaxies reside. That's curious, because one might expect that galaxy interactions, which can trigger starbursts, would happen more frequently in denser regions. Yet BCDGs are more often located in cosmic voids, the vast empty regions between galactic filaments. This isolation might help preserve their gas, preventing it from being stripped away by the gravitational forces or heated plasma of nearby massive galaxies. But it also deepens the mystery. If they're alone, what's triggering their starbursts? Some theories suggest that even minor disturbances, like the infall of a gas cloud or the gravitational nudge of a passing dwarf, might be enough to set off a chain reaction of star formation. Others propose that internal processes, such as the dynamics of dark matter within the galaxy, might be responsible. Whatever the cause, the fact that these galaxies can ignite such intense activity in such quiet environments adds another layer to their puzzling nature. Speaking of dark matter, BCDGs are also relevant in the ongoing investigation into one of the universe's biggest unsolved problems: their rotation curves. How the speed of stars changes as you move outward from the center, don't always match what you'd expect based on visible matter alone. That suggests a hidden component, something that adds mass without emitting light, dark matter. Because these galaxies are relatively simple systems, they're actually easier to model than large spirals or ellipticals, making them ideal for testing dark matter theories. Some observations hint that BCDGs may have dark matter halos that extend well beyond their visible boundaries. If we can better understand how dark matter is distributed in these galaxies, it could help us refine our larger theories of how dark matter behaves, and what it might be made of. Another fascinating angle is the role of feedback in BCDGs. In astronomy, feedback refers to the way that energy and matter released by stars, especially massive stars and supernovae, affect the surrounding gas. In massive galaxies, feedback is a crucial regulator of star formation. It can blow out gas, suppress new stars, and shape the overall evolution of the system. But in blue compact dwarf galaxies, feedback seems to behave differently. Despite massive starbursts and supernova activity, these galaxies often retain a lot of their gas. That resilience is surprising and suggests that our models of feedback may need revision, especially when applied to small, low-mass systems. It also opens up questions about how feedback works in the early universe, where galaxies were smaller and more numerous. By studying BCDGs, we might gain insight into how the first galaxies managed to hold onto enough gas to continue forming stars, even in the face of violent internal processes. Then there's the puzzle of their origin. Are BCDGs young galaxies just now forming stars for the first time? Or are they older systems experiencing a kind of rejuvenation, a second, or third, or fourth wave of star formation after a long dormant period? Evidence exists for both scenarios. Some BCDGs show signs of older stellar populations hidden beneath the bright blue glare of newly formed stars. That would suggest they're not truly young, just experiencing a temporary burst. Others, however, seem to lack any trace of older stars, pointing toward a genuinely new galaxy, perhaps assembled from primordial gas clouds that never got around to forming stars until recently. If the latter is true, it means that galaxy formation might still be happening today, in a universe over 13 billion years old. That's an exciting prospect, and one that could radically reshape our understanding of cosmic history. These galaxies also show us how different the universe looks depending on what you're trying to see. In visible light, a blue compact dwarf galaxy might appear as a small, bright smudge. But if you observe it in radio wavelengths, you might see enormous envelopes of neutral hydrogen gas extending far beyond the visible component. In ultraviolet, you see the fierce glow of newborn stars. In infrared, you might detect warm dust heated by star formation. Each wavelength tells a different story, and only by combining them can we get a full picture of what's really going on. This multi-wavelength approach is essential, not just for understanding BCDGs, but for grasping the universe as a whole. It reminds us that what we see is always just a part of the bigger picture, and that many of the universe's secrets are hidden in light we can't see with our eyes alone. Like the infall of a gas cloud or the gravitational nudge of a passing dark matter filament, could be enough to set off a chain reaction within these galaxies. It wouldn't take much to compress some of the cold gas floating within a BCDG. A tiny shockwave, a minute ripple through the interstellar medium, or a subtle tug of gravity could compress just enough hydrogen to start the process of collapse. Once one star forms, the radiation and pressure it releases can push surrounding gas into new collapses, lighting up vast regions in a domino effect. This would explain how such seemingly quiet and isolated galaxies can suddenly flare up with furious star-forming activity. And it reinforces the idea that the universe, even in its quietest corners, is never truly still. Every particle of gas and dust is always subject to some kind of force, some kind of interaction, no matter how subtle. Some BCDGs also seem to be experiencing cycles, periods of intense star formation followed by quieter phases. That rhythm suggests an internal mechanism might be at work. One possibility is feedback from the stars themselves. When a burst of star formation occurs, the massive young stars quickly evolve and explode as supernovae. These explosions don't just end the lives of stars, they reshape the galaxy's future. The energy they release can blast apart clouds of gas, stopping star formation in its tracks. But as time passes and the debris cools, the galaxy begins to settle again. Gas can start to condense once more, setting the stage for another round of starbirth. It's a cosmic heartbeat, pulsing over tens or hundreds of millions of years. And it might be one of the keys to understanding why blue compact dwarf galaxies behave the way they do. Their chaotic, lopsided shapes, their variable brightness, their erratic cycles of activity, they might all be signs of this ongoing feedback loop. Another mystery is their surprising brightness. For such small galaxies, BCDGs can shine incredibly bright in ultraviolet and blue light. That glow comes from the massive, hot, young stars they're filled with, but there's more to it. Some of these galaxies produce more light than expected for their mass, suggesting they're unusually efficient at turning gas into stars. That's strange, because most galaxies, especially small ones, aren't particularly efficient in this way. Many galaxies have vast reservoirs of unused gas, and star formation is a slow, drawn-out process. But in a BCDG, things happen fast and explosively. One idea is that their compactness allows gravity to work more effectively, pulling gas together quickly and leading to rapid bursts of star formation. Alternatively, some scientists think we may be underestimating the role of turbulence in these galaxies. Instead of being stable, rotating disks like larger galaxies, BCDGs are often turbulent, with gas moving in complex, chaotic flows. That turbulence might help compress gas into stars more quickly than gravity alone would allow. The metallicity of BCDGs is another clue. Metallicity, in astronomy, refers to the presence of elements heavier than hydrogen and helium. In stars and galaxies, metallicity can tell us a lot about age and evolution. Most young galaxies from the early universe have very low metallicity, because heavier elements hadn't yet been created in large quantities. Over time, successive generations of stars fuse hydrogen into heavier elements and spread them throughout the galaxy through winds and supernovae. That raises the overall metallicity. So, when astronomers find BCDGs with unusually low metallicity, they take notice. It might mean these galaxies haven't formed many stars yet, or they've somehow lost much of the enriched material created by earlier stars. Either way, it suggests that some BCDGs are chemically primitive, which is surprising for objects that exist in the modern universe. They could be living fossils, holding on to the traits of the very first galaxies that formed after the Big Bang. And yet, not all BCDGs are alike. In fact, they may represent a wide variety of galactic histories that happen to result in similar appearances. Some may be ancient galaxies that have only recently started forming stars again. Others could be the result of dwarf galaxy mergers. Some might have formed from gas clouds that never coalesced into larger systems. That diversity is part of what makes BCDGs so fascinating. They blur the lines between different categories of galaxies. They don't fit neatly into our models. And that confusion is a clue in itself. In astronomy, the things that don't make sense often lead us to the biggest discoveries. When something doesn't fit, it usually means we're missing a piece of the puzzle. And blue compact dwarf galaxies are full of missing pieces. They also challenge our understanding of how galaxies grow and die. The standard model suggests galaxies start small and grow over time through mergers and accretion. Eventually, they may run out of gas or become stabilized by their own mass, slowing down star formation and fading into quiescence. But BCDGs seem to buck that trend. Some are small but hyperactive. Others are old but suddenly flare to life again. They seem to resist a single narrative. Instead of fitting into a clean timeline, they exist in the gaps, between early and late, between active and passive, between primitive and evolved. That in-between nature makes them harder to study but more rewarding when we do. Because every BCDG we look at might be showing us a different side of the galaxy life cycle. Some are like newborns, just starting to shine. Others are like reawakened elders, sparking one last blaze of light before fading. And some might be completely outside our usual timelines altogether, formed in isolation, evolving on their own terms, connected more to the web of cosmic gas than to any other galaxy. One idea is that their compact structure allows energy and momentum from young stars to cycle through the galaxy more efficiently. In larger galaxies, energy from supernovae or stellar winds might get lost in the vastness of space. But in a tiny BCDG, that energy stays local. It shakes things up, compresses more gas, and sets off more star formation. It's a feedback loop operating in overdrive, one that may be largely unique to galaxies of this size and density. This could explain why some of them burn so brightly in their blue phase. It's not just that they're forming stars, it's that they're doing it fast, all at once, and without the usual inefficiencies that bog down larger systems. Now let's take a moment to think about what that really means. Imagine a galaxy the size of a fraction of the Milky Way, suddenly erupting into life like a firecracker in the dark. It wasn't bright before, barely noticeable in the vast sea of space. But now, ultraviolet light is pouring out of it. Massive stars are forming in tight clusters. Nebulae glow in all directions. To us, it appears as a compact but blazingly active dot through our telescopes. But inside it, immense forces are in motion. It's the kind of transformation that, if it happened nearby, could reshape the interstellar environment of entire star systems. And yet, in the depths of the cosmos, it's just another anonymous flicker among billions. But there's another part of the story that adds more mystery. The stars inside many BCDGs are extremely low in what's called metallicity. In astronomy, anything heavier than helium is called a metal. Our Sun, for example, has a decent amount of metals because it's a second-generation star. Earlier stars went supernova and seeded the gas it formed from with heavier elements. But in BCDGs, especially the more extreme ones, the gas is almost completely primordial, pure hydrogen and helium, virtually untouched by previous generations. That alone is enough to raise some eyebrows. Because if the gas is so primitive, it means these galaxies haven't undergone much recycling. It hints that their star formation history might be very short, or very sparse until now. That begs a question. Are we seeing these galaxies during their first ever major episode of star formation? Could it be that they've been sitting idle for billions of years, never reaching the right conditions to form stars, until some recent trigger flipped the switch? If that's the case, then observing them now is like catching lightning in a bottle. We're seeing a galaxy in the exact moment it wakes up from cosmic slumber. Not just forming stars, but doing it with raw, untouched gas that's barely changed since the early universe. That's rare, and it makes BCDGs incredibly valuable to astronomers. They're time capsules, living examples of how the earliest galaxies might have behaved when the universe was still young. Even more interesting is that some BCDGs are almost completely isolated. They're not part of clusters. They're not orbiting bigger galaxies. They're just floating out in intergalactic space, away from the gravitational drama that defines much of the cosmos. And yet, despite that quiet solitude, they explode with star-forming fury. That's puzzling because most star formation we see is triggered by interactions, galaxies bumping into each other, stealing gas, shocking clouds into collapse. But in these isolated BCDGs, that's not the case. Whatever's driving their activity must be internal. It might be turbulence in their gas, a delayed gravitational collapse, or even cold accretion streams feeding them from the cosmic web. Each of those scenarios opens up a world of possibilities and questions. It also hints at something deeper. Maybe blue compact dwarfs aren't just anomalies. Maybe they're reminders that the universe still has surprises in store, even in the most unassuming places. In fact, BCDGs might be some of the last galaxies still undergoing the kinds of processes that were common in the early universe. Back then, nearly all galaxies were small, chaotic, and rich in pristine gas. If BCDGs are still forming stars in the same way, then studying them is like looking back in time, not metaphorically, but in behavior. That makes them perfect laboratories for understanding galaxy formation. Not the slow, mature kind we see in spiral galaxies today, but the wild, unpredictable kind that existed in the first billion years of the cosmos. And then there's their future to consider. What happens after the starburst ends? BCDGs don't have a lot of mass, so their gravity isn't strong enough to hold on to all the energy and radiation produced by new stars. Much of that energy escapes into space. Sometimes, so does the gas. A few powerful supernovae could be enough to blow out most of the remaining hydrogen in the galaxy. When that happens, the galaxy has nothing left to make new stars. It slowly dims, its brilliant blue light fading to black. All that remains is a faint, ancient collection of low-mass stars drifting through the void. It's a dramatic transformation, from a furious blaze of creation to quiet darkness in just a few 100 million years. For something so small, a BCDG can live fast and die young. But not all of them die. Some BCDGs might settle down after their first major starburst, hold on to enough gas, and enter a quieter phase of life. They could form stars at a slower pace for billions of years. Their intense blue glow would fade into a softer white. Over time, they might even attract other small galaxies and grow into something bigger. That possibility makes them even more interesting, because they're not just relics of the past. They could be the seeds of future galaxies. Little engines of change scattered across the universe, ready to evolve into something much larger if conditions allow. And as always, the biggest mystery isn't what we know. It's what we don't. BCDGs challenge a lot of our assumptions about galaxy formation. They show us that size doesn't always mean complexity. They remind us that dramatic processes can happen even in the smallest, quietest corners of the cosmos. They raise questions about timing, about triggers, about evolution. And they prove that the universe is still very much alive. Even billions of years after the Big Bang, there are still places where stars are being born for the very first time. That thought alone should be enough to keep astronomers staring at the sky for decades to come. Stars, until now? It's a wild thought. Galaxies that have existed for most of the age of the universe, silently floating through space, filled with cold gas but barely forming stars, suddenly igniting into life like cosmic late bloomers. And it isn't just one or two of them. Astronomers have found dozens, possibly hundreds, of these blue compact dwarf galaxies. Some are nearby, part of our local galactic neighborhood. Others are billions of light years away, showing us what the early universe looked like. But whether they're near or far, they seem to follow the same script: small, gas-rich, metal-poor, and suddenly bursting with blue light from young stars. But that's not where the mystery ends. Some BCDGs don't even look like regular galaxies. They have distorted shapes, off-center starbursts, tails of gas, irregular blobs of matter clumped together. It almost looks like they were smashed together by something, or pulled apart. This opens up another theory, that some BCDGs are the result of mergers between even smaller dwarf galaxies. Think about it. Two small galaxies drift close together, gravity pulls them into a collision, their gas clouds compress, and suddenly, boom, a wave of star formation is triggered. It's like two dry logs rubbing together until they spark a fire. That fire becomes the starburst that defines a blue compact dwarf galaxy. And then there's the dark matter problem. These galaxies are small, yes, but they don't behave like they should based on their visible mass alone. Their stars orbit faster than expected, and they seem to hold on to gas that other small galaxies would have lost long ago. That hints at large amounts of dark matter, an invisible form of mass that doesn't emit or absorb light but has gravity. Without it, the galaxies might not hold together. They might fly apart after one big starburst. But with it, they remain intact, even after repeated rounds of intense star formation. If BCDGs are packed with dark matter, they could be miniature laboratories for studying how dark matter works in the real universe, not in simulations, but in observable objects we can track over time. Another thing that makes scientists scratch their heads is how rare these galaxies actually are. You'd expect to see lots of small galaxies because, in theory, they should be the most common. But finding blue compact dwarf galaxies actively bursting with new stars is surprisingly uncommon. That raises the possibility that this stage in their evolution is brief, a flash in the cosmic pan. Maybe they spend most of their lives quiet, faint, and undetectable. Then, for a few million years, they erupt in blue light, form thousands of stars, and then fade back into the dark. If we happen to catch them during that brief window, it's a lucky break. But it also means we might be missing a huge number of them that aren't currently lit up. It's like walking through a forest at night and occasionally seeing a firefly blink. Each flash is brief and beautiful, but between the flashes, the insect is still there, just invisible to your eyes. If blue compact dwarf galaxies are like cosmic fireflies, the universe may be filled with them, but we only notice the ones that are currently glowing. Then there's their role in cosmic history. Some researchers believe BCDGs may be analogues of the very first galaxies that ever formed after the Big Bang. Back then, the universe was filled with hydrogen and helium, but almost no heavier elements. The first stars, called population 3 stars, would have formed from this pristine material. If BCDGs are forming stars from nearly pure gas even today, they might be doing something similar to what those first galaxies did. In other words, studying BCDGs could be like peeking back in time, into the cosmic dawn. But here's the catch. Those first galaxies are too far away and too faint to study directly with our current telescopes. So blue compact dwarf galaxies might be our best stand-ins, our most accessible clues to what the early universe was really like. By watching them, we might be unlocking secrets that go back more than 13 billion years. Their compact size, primitive gas, intense star formation, all these things mirror what astronomers think the first galaxies might have been like. They're not just cosmic curiosities. They're windows into a chapter of the universe we've never truly seen. And yet, the more we study them, the more questions pop up. Why do only some gas-rich dwarf galaxies turn into BCDGs? What triggers the starburst phase in the first place? Is it a random collision? A close pass by another galaxy? Or something internal, like a slow buildup of pressure and density in the gas clouds? Even after decades of observation, we don't fully understand the mechanics behind it. Each new BCDG discovered adds to the puzzle rather than completing it. And what happens after the starburst fades? Do these galaxies go dormant again, waiting for the next trigger? Or do they burn through all their gas and die out as small, faint clouds of old stars? Some astronomers think they might evolve into different kinds of dwarf galaxies over time, perhaps becoming dwarf ellipticals or irregulars, depending on how much gas remains. Others think the cycle could repeat, with the galaxy returning to a quiet phase until another event restarts the process. It's still an open question, and the answers might vary from one BCDG to another. Incredibly short-lived. Maybe the blue, starburst phase only lasts a few tens of millions of years, which, in cosmic terms, is like the blink of an eye. If that's true, then we're catching these galaxies during a very specific, very rare moment in their lives. It's like walking into a forest and seeing a tree just as it bursts into bloom. You'd assume it always looks like that, but in truth, it's just one part of a much longer cycle. That brings us to one of the biggest unknowns about blue compact dwarf galaxies. What happens to them after the burst is over? Do they quiet down and go dark? Do they become regular dwarf galaxies, faint, red, and filled with old stars? Or do they continue in cycles, bursting into life every few 100 million years when conditions are right? Some astronomers think they might evolve into elliptical dwarf galaxies once their star-forming fuel runs out. Others believe they could fade into almost invisible ghost galaxies, drifting silently in the universe, barely giving off any light. And some might eventually merge with larger galaxies, losing their identity entirely. Yet, despite all the unknowns, blue compact dwarf galaxies could hold the keys to some of the biggest cosmic puzzles. For one, they could help us understand how the first galaxies in the universe formed and evolved. Early galaxies were small, metal-poor, and chaotic, just like BCDGs. So by studying these modern-day versions, astronomers can piece together what the universe looked like when it was just a few 100 million years old. It's like finding fossils that match what we expect from prehistoric creatures, but alive and active today. And here's another wild idea. Some scientists think that BCDGs might be the building blocks of larger galaxies. In the early universe, galaxies grew by merging together, small ones joining to form big ones. If BCDGs are relics of that time, then maybe we're seeing the leftover pieces that didn't get swallowed up. Maybe the Milky Way itself was once made of dozens or even hundreds of BCDG-like structures, all merging over billions of years to become the massive spiral we live in now. And then there's the connection to reionization, the ancient era when the first stars and galaxies lit up the universe and reionized the neutral hydrogen fog that filled space. Some researchers believe that small galaxies, especially ones like BCDGs with lots of intense star formation, could have been the major contributors to this cosmic transformation. That's a huge deal. It means that even though these galaxies are small, their impact on the early universe might have been enormous. But here's the twist, not all BCDGs are the same. Some have smooth, central starbursts. Others have chaotic, scattered clusters of newborn stars. Some have large halos of old stars surrounding the bright blue core, while others are almost entirely young. Some seem isolated, drifting alone in deep space, while others are caught in the gravitational web of galaxy clusters. Why such a wide variety? Are we looking at different stages in a single process, or are there multiple paths that lead to what we call a blue compact dwarf galaxy? And what about the role of environment? Galaxies don't live in a vacuum. Well, technically they do, but you know what I mean. They're influenced by their neighbors, by intergalactic gas, by cosmic filaments, and more. Some BCDGs are found near larger galaxies, possibly triggered into starbursts by gravitational encounters. Others seem to be in the middle of nowhere, which raises even more questions. What triggers a starburst in an isolated galaxy? Could it be internal processes, like the collapse of gas clouds, or invisible interactions with dark matter substructures? The truth is, we don't fully understand what causes these galaxies to suddenly wake up and start forming stars. It might be mergers. It might be gas accretion. It might be turbulence, magnetic fields, or something we haven't even discovered yet. What we do know is that these galaxies are incredibly efficient once they get going. Their star formation rates, relative to their size, are off the charts. That means they're burning through their gas at a breakneck pace, which brings us back to that earlier point: this phase can't last forever. In fact, some BCDGs seem to be running out of fuel already. Observations show that they don't have enough gas to keep forming stars at the same rate for much longer. So unless they somehow get more gas, maybe by pulling it in from intergalactic space or from surrounding clouds, they'll eventually fade. That's why astronomers think we're catching these galaxies during a very short, very intense chapter of their lives. A cosmic fireworks show, bright and beautiful, but brief. Still, the idea that some BCDGs are undergoing multiple bursts of star formation, separated by long periods of calm, is gaining traction. In that case, maybe they aren't one-hit wonders after all. Maybe they go through cycles, like breathing in and out. They gather gas, compress it, form stars, expel energy, and then rest, only to do it all over again after a few 100 million years. That would explain why we see some with traces of older stars mixed in with young ones. And it would mean that these galaxies are more resilient and complex than we thought. Another thing that's fascinating about BCDGs is their simplicity, and how that simplicity can help solve big astrophysical problems. Because they're small and relatively isolated, they don't have the messy complications of big galaxies. No sprawling spiral arms, no massive black holes at the center, no complex histories of hundreds of mergers. That makes them perfect for testing theories. They're like a clean laboratory for understanding how stars form, how galaxies evolve, and how cosmic processes work on a small scale. And because they're so metalpolar, meaning they lack the heavier elements created by older generations of stars, they resemble the conditions of the early universe. By studying the stars and gas in BCDGs, astronomers can test their models of stellar evolution, nucleosynthesis, and chemical enrichment. It's like rolling back the clock and watching how things were in the first billion years after the Big Bang. But even with all these insights, we're still just scratching the surface. New telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are already starting to uncover even more details about BCDGs, including ones that are so distant, we're seeing them as they were billions of years ago. As these instruments look deeper and with greater clarity, we might finally start to untangle the mystery of how these strange little galaxies came to be, and what they're trying to tell us about the universe itself. Imagine a time when the universe was completely dark, filled with a thick soup of neutral hydrogen that absorbed light like a fog. Then, the first stars and galaxies ignited, pumping out intense ultraviolet radiation. Slowly, this light began punching holes through the darkness, ionizing the hydrogen and making the universe transparent. This epoch, known as the era of reionization, is one of the most mysterious and important chapters in cosmic history. But we still don't fully understand how it happened or what drove it. Blue Compact Dwarf Galaxies might be a missing piece of that puzzle. Their intense bursts of star formation, high-energy radiation, and simple structure make them excellent analogs for the first galaxies that ever existed. If these small but powerful galaxies were common in the early universe, and there's good reason to believe they were, they could have been responsible for much of the reionizing light. The fact that modern BCDGs can still blow out gas and light into their surroundings suggests that early galaxies might have done the same, helping to reionize the entire universe one tiny, glowing island at a time. But as we look deeper, another strange question arises: why don't we see more BCDGs today? If they were once so common, where did they all go? Have they all merged into bigger galaxies? Did they simply run out of gas and fade away? Or could there be thousands of them still out there, hidden by distance or cosmic dust, waiting to be discovered? Astronomers are working hard to answer these questions. With new instruments like the James Webb Space Telescope, we're finally able to peer into the farthest reaches of the universe, where ancient galaxies glow from billions of years ago. Some of the faint, distant galaxies being discovered may actually be early versions of BCDGs, frozen in time. Each observation adds a piece to the puzzle, helping us trace the story of galaxy formation from the earliest spark to the complex structures we see today. And still, for all we've observed, BCDGs continue to defy simple explanations. They're chaotic and unpredictable. Some are surrounded by vast envelopes of gas, others seem oddly isolated. A few seem to rotate, others don't. Some are formed in clusters, others float alone in deep space. It's like studying wild animals in nature. No two are exactly alike, and the rules that apply to one may not apply to the next. This diversity is both frustrating and fascinating. It suggests that blue compact dwarf galaxies are not just one thing. They might represent many different paths of galactic evolution. Some could be young, forming stars for the first time. Others might be old galaxies experiencing a final, desperate burst of activity. Some might be shaped by collisions, others by internal instabilities. And all of this adds to the mystery. We can't even be sure we're looking at one class of object. We might be lumping together different things simply because they look similar at first glance. That's the danger and the beauty of astronomy. What we see is just the surface. The deeper we look, the more we realize how little we understand. Blue compact dwarf galaxies may seem small, but they contain the echoes of cosmic history. They reflect the wild, untamed energy of the early universe and challenge everything we thought we knew about how galaxies grow, evolve, and die. Their strange properties, low metallicity, intense starbursts, chaotic structures, could be clues to forces we haven't yet uncovered. They might be showing us what happens when dark matter clumps in unusual ways. They might reveal how gas flows in and out of galaxies on massive scales. Or they might simply be cosmic accidents, freak objects that defy patterns because the universe is far more random than we'd like to believe. But what's certain is this: blue compact dwarf galaxies matter. They aren't just oddballs or outliers. They're keyholes into the past. They help us understand the conditions that shaped everything, from the tiniest star to the largest galactic cluster. And as we learn more about them, we're not just learning about galaxies, we're learning about the very nature of the cosmos itself. Might actually be a broad category that includes multiple types of small galaxies undergoing different kinds of evolution. Some could be newly formed galaxies, just lighting up for the first time. Others might be ancient relics, temporarily reigniting with bursts of star formation triggered by galactic collisions or infalling gas. Still others could be transitioning into completely different types of galaxies, like dwarf ellipticals or irregulars. The variety we see in BCDGs could be a sign that they're not a final form, but a phase in a much longer and more complicated story. What makes them especially interesting is that they often live in environments where we wouldn't expect such activity. Some are found in relatively empty regions of space, far from massive galaxies that could trigger starbursts through gravitational interactions. This hints at internal mechanisms, maybe the collapse of gas clouds, or cycles of gas outflows and inflows, that could fuel these explosive episodes all on their own. In contrast, others are located near galaxy clusters, where their starbursts might be induced by interactions, mergers, or tidal forces from neighboring galaxies. This environmental contrast opens up more questions than answers and shows that the same kind of galaxy can evolve in very different ways depending on where it exists in the universe. And then there's the question of dark matter. Like most galaxies, BCDGs appear to be embedded in halos of invisible mass that shapes their motion and structure. But measuring dark matter in these tiny systems is incredibly difficult. Some BCDGs rotate fast enough to imply the presence of massive dark halos, while others appear to have very little rotation at all. This inconsistency could be a clue to how dark matter behaves on small scales, or it could reveal that we're missing key physics in how gas, stars, and gravity interact in these galaxies. Either way, BCDGs might be one of our best laboratories for testing dark matter theories, because their small size strips away many of the complications seen in bigger galaxies. Another strange property of many BCDGs is their surprisingly low dust content. In most galaxies, dust plays a crucial role. It absorbs and re-emits starlight, influences star formation, and shapes how we observe light from across the cosmos. But in BCDGs, especially the most metal-poor ones, there's far less dust than we'd expect. This lack of dust makes them more transparent, allowing us to directly observe the hot, young stars and ionized gas inside. It also suggests that these galaxies haven't had time, or the right conditions, to build up large quantities of dust through generations of stars. This nakedness gives astronomers a clearer look at starburst processes, but it also raises new puzzles. How do stars form so rapidly in environments without much dust to shield and cool the gas? How does the lack of dust affect the temperature and pressure inside the galaxy? Every time we try to answer one question, 3 more appear. Let's not forget the role of supernovae. In such compact, gas-rich environments, the death of a massive star can unleash catastrophic energy. One supernova can send shockwaves through the galaxy, compressing clouds into new stars, or blowing them apart. In BCDGs, where hundreds of massive stars might form in a short time, this process is happening on a massive scale. Whole regions of gas can be ionized, stripped, or ejected entirely from the galaxy. These superwinds can reshape the galaxy's future, regulating how many stars it will form next, or how long its current starburst will last. In some cases, the supernova-driven outflows may be so intense that the galaxy expels much of its gas into intergalactic space, potentially ending its star-forming days altogether. This cycle of creation and destruction, powered by supernova feedback, makes BCDGs feel alive, constantly changing, reacting, and evolving in response to the violence within. And this leads us to one of the most haunting ideas. What if BCDGs are just the brief visible flare-ups in a longer, quieter life cycle? A galaxy could go through long periods of dormancy, quietly drifting in space, until a trigger, gas infall, tidal interaction, or even a small merger, suddenly reignites star formation. For a few million years, the galaxy lights up, becoming a BCDG. Then it fades again, going dark for hundreds of millions of years. If that's true, then BCDGs aren't rare, they're just hard to catch. We're only seeing them during their loudest moments, like spotting a volcano mid-eruption. The rest of the time, they hide in plain sight, unnoticed. This also suggests that the population of galaxies in the universe is far more dynamic than we usually think. Instead of fixed categories, spiral, elliptical, irregular, we might need to think in terms of phases and transformations. Galaxies might move back and forth between types depending on what happens to them. BCDGs could be a temporary phase that many galaxies pass through at some point in their lives. This challenges how we catalog and study galaxies and forces us to think less in terms of classification and more in terms of processes. What matters is not just what a galaxy is, but what it's doing and where it's going next. Some of the most distant galaxies ever observed, those seen as they were just a few 100 million years after the Big Bang, look suspiciously like BCDGs. They're small, intensely blue, and full of young stars. Their light has traveled for over 13 billion years to reach us, and yet their structure and behavior mirror the BCDGs we can study up close in the nearby universe. This isn't just a coincidence. It could mean that by studying BCDGs nearby, we're looking into a cosmic mirror, seeing how galaxies behaved at the dawn of time, and learning about conditions in the early universe that no telescope could observe directly. And now, the field is about to explode with new data. The James Webb Space Telescope is already opening windows into the deep universe, revealing faint galaxies with precision we've never had before. Future missions like the Nancy Grace Roman Space Telescope and the Euclid mission will map galaxy structure across the cosmos, searching for dwarf galaxies and low-mass systems with unprecedented sensitivity. Every one of these new instruments brings us closer to unraveling the mysteries of blue compact dwarf galaxies. Are they ancient relics or newborn systems? Are they common or rare? Are they isolated freaks or universal building blocks? We're starting to realize that there's no simple answer. The universe is full of complexity, and BCDGs are no exception. They challenge our models, defy our predictions, and resist easy explanations. But that's what makes them so important. Because every time we're forced to revise our understanding, we get a little bit closer to the truth of dust through the typical life cycles of stars. This scarcity of dust creates a clearer view of the energetic processes taking place, which is rare and valuable in observational astronomy. It also raises a fascinating question. Are we looking at a window into what early galaxies were like before they had time to accumulate dust and metals? If so, blue compact dwarf galaxies could be cosmic relics that bridge the gap between the very first galaxies and the complex ones we see around us today. They might not just be interesting because of their compact size or starbursts. They might be fossil records of the universe's youth. But despite how revealing they can be, BCDGs are also incredibly challenging to study. Their small size means they're faint, especially when compared to the vast and luminous spiral or elliptical galaxies that dominate most surveys. They often go unnoticed in broad sky surveys unless they're undergoing a major starburst that lights them up. That means we might be missing a huge number of these galaxies, hidden in the dark corners of the cosmos, quietly shaping the evolution of the universe without drawing much attention. And because of their small size, many of their internal details are blurred when seen from Earth. We need the sharpest telescopes and deepest observations to pull out the structure of these galaxies, how gas moves inside them, how stars form and die, how dark matter is distributed, and how these pieces all interact. And then there's the role these galaxies might play in cosmic reionization, the period in the early universe when the first stars and galaxies began reionizing the neutral hydrogen that filled space after the Big Bang. Some scientists think that galaxies like BCDGs, with their high-energy starbursts and low dust content, could have been major contributors to that process. Their light would have been less absorbed by dust and more likely to escape into the universe, helping to reionize vast volumes of hydrogen. Studying today's BCDGs could be our only real way to understand how that happened. If we can figure out how much energy escapes these galaxies, and under what conditions, we can begin to answer one of the most important questions in cosmology. How did the universe become transparent? Another point worth considering is how resilient these galaxies are. Despite undergoing intense bouts of star formation, some strong enough to blow away significant amounts of their gas, many BCDGs manage to survive and continue forming stars. They don't get ripped apart easily. That's surprising, given their low mass and shallow gravitational potential. A big enough starburst should, in theory, eject their gas and shut them down. But over and over again, we find BCDGs that seem to bounce back. Maybe they pull in new gas from the cosmic web. Maybe they're held together more strongly than we thought, possibly by dark matter. Or maybe they cycle through periods of activity and dormancy in a way that we don't yet understand. Whatever the answer, these galaxies seem tougher than they look. And it's not just the gas and stars that are mysterious, it's the structure of these galaxies too. When astronomers observe them in detail, BCDGs often don't have the smooth, organized shapes we associate with more mature galaxies. Instead, they're messy. Some have irregular clumps of stars scattered throughout. Others show signs of rotation, but not always in a way that matches their shape. Some are nearly spherical, others elongated or lopsided. This structural chaos might be the result of recent mergers or close encounters with other galaxies. Or it might reflect their early formation history. Perhaps they formed without the orderly rotation seen in spiral galaxies, instead growing through chaotic, clumpy accretion of gas. Either way, their shapes tell us something about the early processes that governed galaxy formation. Understanding how order arises from such disordered beginnings could be key to understanding all galaxies. Even more compelling is the fact that some blue compact dwarf galaxies host massive star clusters, compact regions filled with thousands, or even millions of young stars. These clusters resemble what astronomers call superstar clusters, or even protoglobular clusters. And that's important, because globular clusters are ancient structures found in almost every large galaxy, including our own Milky Way. They're made of some of the oldest stars in the universe, but we don't fully understand how they formed. By studying similar clusters in BCDGs today, we might be witnessing the same processes that formed globular clusters billions of years ago. These galaxies might not just be analogs of early galaxies. They could be actively recreating the conditions of the early universe in real time. And then there's the chemical side of the story. Because BCDGs have low metallicity, they're like time capsules for studying the chemical evolution of the universe. Metals, elements heavier than hydrogen and helium, are made in stars, so low metallicity systems are typically either very young or have had very inefficient star formation. In either case, their chemical makeup gives us insight into what kinds of elements existed early in the universe, before stars had time to create and distribute heavier atoms. This has huge implications for understanding how the first stars formed, what kinds of planets might exist in such environments, and even how life could emerge in galaxies very different from our own. Their chemical simplicity also makes them great testbeds for models of stellar evolution. In metal-rich environments like the Milky Way, stars lose mass more easily through winds and radiation. But in metal-poor galaxies like BCDGs, stars retain more of their mass, evolve differently, and may end their lives as different kinds of supernovae. Observing these stars in action helps us test and refine our models, making our understanding of stellar physics more accurate across a wider range of environments. In this way, Blue Compact Dwarf Galaxies help not just cosmology, but nearly every branch of astronomy. Even as we gain more data from space-based observatories like Hubble, and soon with the James Webb Space Telescope and future missions like the Nancy Grace Roman Space Telescope, BCDGs remain hard to pin down. Every time we think we've found a pattern in their behavior or a theory that fits all the observations, new data shakes things up. One BCDG will behave like a pristine early galaxy, another will show signs of multiple starburst cycles, and a third might exhibit strange motions or interactions with invisible companions. It's this diversity that keeps astronomers coming back. These galaxies might be small, but they contain multitudes, each one a laboratory of physics, chemistry, and evolution wrapped into a single chaotic system. Some researchers are even exploring the idea that BCDGs might represent a fundamental stage of galaxy formation, one that every galaxy passes through at least once. According to this view, massive galaxies like the Milky Way could have formed from the merger and growth of dozens or even hundreds of such dwarf systems. If that's true, then studying BCDGs today is like traveling back in time to the building blocks of cosmic structure. They might be among the most important pieces of the universe's grand puzzle, not just curiosities on the fringe of astronomy, but central players in the history of everything we see. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.